University of South Australia, Australia.
The fourth is Professor Marko Fauvonen from University of Eastern Finland, Finland.
Excellencies, the Dean of Faculty of Mathematics and Natural Science, University of Jember, Dr. Andes Ahmad Saifullah, PhD.
Excellencies, President of Indonesian Mathematical Society, Professor Dr. Indah Emilia Wijayanti.
And also, we welcome all the presenters and participants of the first IC-MaGeStiC 2021.
The praise of our gratitude to the Almighty God for His wisdom and grace, so that the first IC-MaGeStiC can be held today on November 27, 2021.
This conference is an excellent forum for researchers, lecturers, educators, and students to exchange ideas, to communicate and discuss research findings and new advances in mathematics and science education.
Besides that, this conference is also aimed to enhance our network for further collaboration between researchers from the countries in the region and those from outside the country.
Excellencies, participants, ladies and gentlemen, please let me read our main agenda of this conference. The first agenda is opening ceremony. The second is welcoming and opening speech. Then we are going to the main session, consists of presentations by our keynote speakers and parallel sessions.
Excellencies, participants, ladies and gentlemen, as our welcome greeting with hospitality and respect, we would like to present you a profile video of our department.
This is our Mathematics Department of Faculty of Mathematics and Natural Science, University of Jember.
Welcome to Mathematics Department. The Mathematics Study Program was established in 1997, with its commitment of Jember University to develop basic and formal science. Formally, Mathematics Department was established with approval from Director General of Higher Education, Ministry of National Education of the Republic of Indonesia, through Decree number 99, Decree, Code 2001, concerning Mathematics Department at the Faculty of Mathematics and Natural Science, University of Jember. Mathematics Department has two study programs, namely the Bachelor of Mathematics Study Program, accredited B, and the Master of Mathematics Study Program, accredited B.
Prodi Sarjana Matematika mempunyai visi yang sejalan dengan visi universitas dan fakultas, yaitu menjadi program studi yang berkualitas serta berperan aktif dalam pengembangan dan penerapan matematika, terutama dalam mendukung pertanian industrial. Untuk mencapai visi tersebut, maka kami menetapkan 4 misi program studi matematika, yaitu melaksanakan proses pembelajaran yang berkualitas dan akuntabel, melaksanakan penelitian bidang matematika, terutama yang terkait pada pertanian industrial, berpartisipasi dalam menyelesaikan problematika di masyarakat yang terkait dengan matematika dan penerapannya melalui kegiatan pengabdian, kemudian meningkatkan kerjasama dengan stakeholders dalam penguasaan matematika dan terapannya.
Prodi Magister Matematika FIPA Jember memiliki visi pengembangan keilmuan yang menitikberatkan kepada kemampuan untuk berperan aktif dalam pengembangan ilmu pengetahuan dan teknologi dan memiliki daya saing di tingkat Asia Tenggara. Hal ini akan dilakukan dengan mengembangkan visi, misi ke depan untuk melaksanakan pembelajaran dengan 5 core value. Moto kami bersama Magister Matematika FIPA Jember, we are challenging the future, environmentally literate, and Southeast Asia recognized. Terima kasih.
Minister of Education and Culture, Nadiem Makarim, has launched the Merdeka Belajar Kampus Merdeka MBKM program in 2020. Instead with this program, undergraduates mathematics study program using the MBKM curriculum based on KKNI. In implementing the MBKM curriculum, students can maximize their potential and gain additional competencies through learning activities outside the study program. In addition, the MBKM curriculum also provides opportunity for learners to increase their knowledge in supporting the quality of learning while carrying out the Tridharma of higher education.
Menjadi peserta magang MBKM di Bank Syariah Indonesia merupakan suatu kesempatan besar bagi saya, di mana dari sini saya belajar banyak hal yang tidak saya terima di kegiatan akademik di perkuliahan, seperti pengembangan soft skill, leadership, public speaking, dan masih banyak lagi. Dan saya lebih bisa mengenal bagaimana persiapan untuk dunia kerja ke depannya.
Mathematics Department is supported by resources consisting of 20 lecturers, with qualification of 2 doctoral professors, 7 doctors, and 11 masters. These lecturers have completed further education at several well-known universities, both at domestic and abroad.
To support the learning process and student activities, the Mathematics Department at the Faculty of Mathematics and Natural Science has several facilities and infrastructure, such as lecture room, which is completed by adequate facilities, so that students are comfortable and focused when doing teaching and learning activities. Students can learn independently and discuss with other students by using Mathematics Department facilities in a place that has been provided by the Mathematics Department. No most important, Mathematics Department has provided a reading room with a complete collection of reference books and thesis collections, which can be used by students and lecturers as a place to look for reference. The Mathematics Department at the Faculty of Mathematics and Natural Science also provides administrative room to facilitate students in processing, administration, and files. Student is also provided facility. There is a room which can be used as a gathering place and discussion to study interest or organization activities. Other facilities and infrastructure which can be used for support department events and organizations such as seminar, class lecture, and other activities is Mathematics Department auditorium room.
To support practicum and research activities of the academic community, Mathematics Department also has several laboratories.
Laboratorium Dasar Matematika merupakan laboratorium yang melayani praktikum-praktikum untuk mata kuliah matematika, baik itu di jurusan matematika maupun jurusan-jurusan lain di jurusan Fakultas MIPA Universitas Jember. Selain itu, Laboratorium Dasar juga melayani pelatihan-pelatihan, baik itu pelatihan yang diadakan oleh mahasiswa maupun pelatihan yang diadakan oleh dosen.
Laboratorium Matematika Terapan dan Komputasi jurusan Matematika Fakultas MIPA Universitas Jember merupakan laboratorium yang melayani mahasiswa untuk melakukan penelitian maupun tugas akhir baik dari prodi S1 maupun prodi S2. Laboratorium Matematika Terapan dan Komputasi ini dilengkapi dengan komputer yang berspesifikasi tinggi dengan software-software untuk komputasi matematika dan statistika yang berlisensi resmi.
Laboratorium Geometri Rancang Bangun merupakan satu dari 4 laboratorium yang ada di jurusan Matematika Fakultas MIPA Universitas Jember. Laboratorium Geometri Rancang Bangun mempunyai 2 fungsi utama, yaitu yang pertama melayani mahasiswa jenjang S1 dan S2 untuk menyelesaikan tugas akhirnya dalam bidang geometri, fraktal, dan analisis.
Kelompok riset optimasi dan komputasi matematika merupakan kelompok riset yang beranggotakan dosen jurusan Matematika, Fakultas Matematika dan Ilmu Pengetahuan Alam dengan latar belakang penelitian di bidang komputasi dan optimasi.
Keris Pemodelan Matematika merupakan salah satu kelompok riset yang ada di jurusan Matematika. Dan kita berusaha untuk bagaimana mendekatkan persoalan sehari-hari dalam bahasa matematik untuk diformalisasikan dan disimulasikan kelakuannya lebih lanjut.
Keris Gerbang Mata atau kelompok riset geometri rancang bangun dan matematika analisis merupakan kelompok riset penelitian di jurusan Matematika Fakultas MIPA Universitas Jember yang melakukan kegiatan penelitian dan pembelajaran di bidang geometri rancang bangun dan matematika analisis.
Kelompok riset data scan ingin berkontribusi dalam merubah sudut pandang data riset dan akademik. Kelompok data scan ini dikembangkan sejak tahun 2017. Riset terbarunya tentang interpretable machine learning dilakukan bersama IPB dan Sakuala Aceh sejak tahun 2021 hingga 2023.
The Mathematics Department also has students' organization called IC-MaGeStiC Geocomputation. Students' activities in the Mathematics Department were gathered by several students who became managers of IC-MaGeStiC Geocomputation. There are several activities held by IC-MaGeStiC Geocomputation, such as Limit Mathematics Olympiad, Osaka Scientific Writing Competition, computational training, and several other activities. The activities held aim to improve the ability of the students both in the academic and non-academic fields. Here are some profiles of alumni in Mathematics Department who have successfully graduated and worked in the company they dream of that's suitable with their skills and knowledge that has been obtained during their education in Mathematics Department.
Matematika
Thank you.
For a brief moment of our opening ceremony, we would like to invite you to sing Indonesia Raya anthem. May all we stand up for the people in this room. May all sit straight up. Thank you. Please enjoy your seat.
session. And then we would like to start the next session through a prayer. Please welcome Muhammad Thoriqul Huda, SSI, to lead our opening prayer. Sorry, but your voice cannot be heard.
Oh boy. Voice back.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Success of this virtual conference, may all we pray together. I will lead to prayer in an Islamic way. For the people of other faiths, please adjust according to your respective belief. Bismillahirrahmanirrahim. Alhamdulillahilladzi an'amana bi ni'matil imanil Islam. Wa nusalli wa nusallimi ala khairil anam. Allahumma salli ala sayyidina wa maulana Muhammad wa ala alihi wa sahbihi ajma'in. Allahumma ufir lil muslimina wal muslimat wal mu'minina wal mu'minat al ahya'il minhum wal amwat. Allahumma fir lana wa liwalidayya warhamhuma kama rabbayana shaghira. Allahumma anfa'ni bima 'allamtani wa 'allimni ma yanfa'uni wa zidni ilman. Rabbana la tuzigh qulubana ba'da idh hadaitana wa hab lana min ladunka rahmah innaka antal wahhab. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Subhanaka rabbika rabbil izzati amma yasifun wa 'alal mursalin walhamdulillahi rabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi wabarakatuh. Thank you, Muhammad Thoriqul Huda, SSI.
Excellencies, participants, ladies and gentlemen, we are now going to listen to the welcoming speech delivered by the Chairman of IC-MaGeStiC 2021. Please welcome Dr. Kiswara Agung Santoso. The time is yours.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good morning, distinguished ladies and gentlemen. Today we are proudly hosting the International Conference on Mathematics, Geometry, Statistics, and Computation 2021. Firstly, we would like to thank to the Dean of Mathematics and Natural Science Faculty, Bapak Ahmad Saifullah, PhD, who took their time to come and will to open this conference officially. We would like also thank to the honorable keynote speakers who spend their time to share an invaluable knowledge to us. Don't forget, I would like also to appreciate to all committee to the hard work to make this event run well and success. My respected ladies and gentlemen, in this occasion, the Majestic 2021 is held online due to the COVID-19 pandemic condition. This conference is aimed to bring together scholars, leading researchers, and experts from diverse backgrounds and application area in science. Specialist emphasis is placed on promoting interaction between the science, theoretical, experimental, and other topics related to the mathematics, geometry, statistics, and computation. Good job for all, and thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Kiswara Agung Santoso, for the welcoming speech.
Now, we are going to listen to the opening speech delivered by the Dean of Faculty of Mathematics and Natural Science, University of Jember, to officially open the first IC-MaGeStiC 2021. Ladies and gentlemen, please welcome Dr. Andes Ahmad Saifullah, PhD. Time is yours.
Thank you for the MC. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Selamat pagi. A very early good morning for some participants, maybe from the Europe, as mentioned by the committee. Some participants come from other countries. Good morning, everyone. Your Excellencies, distinguished guests, ladies and gentlemen, I would like to extend a very warm welcome to you all to the International Conference on Mathematics, Geometry, Statistics, and Computation 2021 with the topic Building Network and Collaborative Research on Mathematics Science. First and foremost, I would like to thank to you all, to all participants, especially to invited speaker, and very special to the keynote speaker, Prof. Nobuaki Obata from Japan, Martinus Frederick, PhD from Singapore, and also Professor Marco from Finland, and Professor Fernando from Southern Australia. Ladies and gentlemen, thank you for your participation. You all have allocated their busy time to schedule this and attend to this conference virtually. I would like also express my deepest gratitude to the committee for their hard work and dedication in coordinating and organizing this event. Thank you all. It is truly an honor for me to be given the opportunity to deliver this opening speech, and for our faculty to be the host of such important event. I also very happy to say that this international conference is the fourth conference that we have organized within the past month as part of our celebration on 57th anniversary of the University of Jember and the 21st anniversary of our faculty of Math and Natural Sciences. I'm grateful to your presence here today and to acknowledge that the event is able to engage so many distinguished representatives from many different institutions and countries. I'm certain that the diverse expertise, experiences, and knowledge that you bring here today will be able to complement each other, fill the gaps, and connect the dots that could hopefully answer the burning question on a mathematics and statistics, especially to improve our quality of life. Even though this conference is carried out virtually, and I'm sure it will not stop of us from having a productive discussion. I hope that we can meet again in IC-MaGeStiC for the next year, maybe, or next 2 years, as it is could be a biannually meeting to address more burning question with an offline. We hope we can gathering face-to-face arrangement in Jember, as Jember, like this morning, we have a very bright morning, very nice weather. It's not hot, not cool, very nice. Lastly, before I officially open this meeting on behalf of the chairman of our university, I would like to encourage you active participation throughout this conference, and I hope that through this conference we can effectively collaborate and at the end result in strong synergy between us all. So now, with Bismillahirrahmanirrahim, the 4th International Conference on Mathematics and Statistics, Geometry is officially open. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Dr. Andes Ahmad Saifullah, PhD, for the opening speech.
Ladies and gentlemen, it is time to us entering the plenary session. The main agenda of our conference today, that is the presentations by our keynote speakers. The first keynote speaker is Professor Nobuaki Obata from Tohoku University, Japan, and will be moderated by Dr. Alfi Y. Zakia from Bina Nusantara University. Without further ado, please welcome Professor Nobuaki Obata and Dr. Alfi Y. Zakia. The time is yours.
Thank you. Good morning, ladies and gentlemen. Welcome to International Conference on Mathematics, Geometry, Statistics, and Computation, IC-MaGeStiC. Today, our speaker will be Professor Nobuaki Obata from Tohoku University. Before we begin the talk, I will read briefly curriculum vitae from him. Here, I will share. Okay, Professor Nobuaki Obata, the doctorate education from Nagoya University, and he also do visiting scholar such as University of Tübingen, University of Heidelberg, and many others. And he also the leader in the laboratory mathematical system analysis, editor-in-chief of interdisciplinary information science. Then he also have a publication more than 70 journal papers, and 80 others in proceeding in Japanese. And he also published several books in Japanese and international book here. The international book such as Spectral Analysis of Growing Graph, a Quantum Probability Point of View. Second, Quantum Probability and Spectral Analysis of Graph. And the third, White Noise Calculus and Fog Space. And for today's talk, he will be delivered about quadratic abunding constant of graph. Okay, during the talk, for the participant who have question, can write the question in chat box. Okay, now I will give the time for Professor Nobuaki Obata to deliver his speech. Professor Nobuaki Obata, time is yours.
Okay, thank you very much. Can you hear me?
Yes.
Yeah, okay. Then I'll try to make my presentation. Oh, can you hear this presentation?
Yeah.
That's okay. Oh, thank you very much for your kind introduction, and thank you for your invitation to this very wonderful conference. My concern today is quadratic embedding constants of graphs. By the way, I am coming from Tohoku University in Japan, and it's now quite cool today in Indonesia, and it is not hot, it's not cool, so it's a very moderate temperature, I suppose, but here getting very cool, and maybe snow is coming soon. Anyway, so I chose this topic because, first of all, it is relatively new and maybe interesting for further study. And second, this topic I worked since only 3-4 years, but I collaborated with Indonesian colleagues for this project. And third, this topic belongs to graph theory, discrete mathematics, and analysis. So it is suitable to this conference, I believe. Okay, now I start definition. It's okay, yeah, scrolling is okay. Okay, so I'm going to work on graphs today. Graph is a very simple object in mathematics. It consists of vertices and edges. I usually work on finite graph, but sometimes infinite graph is also okay. So, and also this graph is unoriented, simple, no loops, and connected. So you can imagine such a picture in the Euclidean space. Okay. Now there are many aspects of graphs, but I am focusing on graph distance. So the graph distance, everybody knows, is defined to be the length of a shortest walk from one vertex to others. So in this picture, the graph distance between x and y is exactly 2. So very simple object. And I collect all such data to build up a matrix, which is called a distance matrix. So distance matrix is denoted by D, of which entries are the distances between two vertices. Therefore, this distance matrix has an index set V. Apparently, the diagonal entries are all 0, and this matrix is symmetric in the sense that dxy equals dyx. And those values are all positive integers. whenever x and y are not identical. So it is a very simple object. If you are given graph, you can form distance matrix. It has a lot of data of the graph. Okay, now quadratic embedding constant, which is the main subject of my talk today. Now I consider connected graph, finite or infinite, but mostly I'm working on finite graphs. And D is distance matrix. Now, if you are given the distance matrix, you may associate a quadratic function of this type, f times df. F is just a vector defined on vertex set V, and we consider the maximum value of this quadratic function over certain set. That set is defined by inner product ff equal to 1. It means that f runs over a unit sphere. And the second condition is the inner product 1 and f. Here, 1 is the constant vector of which entries are all 1. And such an inner product is equal to 0. It gives you a hyperplane. Therefore, we consider a unit sphere and cross-section with hyperplane, which is again a sphere of codimension 2. Here, the definition of inner product. So this is just for convenience for audience. This is the usual one. Okay. So now, if you are working on a finite graph, then f runs over just a finite dimension vector. Therefore, this cross-section codimension 2 sphere is compact. Therefore, the quadratic function attains its maximum on that compact set. Therefore, we can replace supremum by max usually. And that maximum value is called QE constant of graph Z. So this is my main object. This was defined by myself some time ago, but I found it may be interesting to study further. So I chose this topic today. Okay, now I'd like to mention some backgrounds and motivations. So maybe it is convenient to trace back to Schoenberg theorem. Here is an old question. Now, suppose we are given a matrix K, n times n matrix, real matrix, okay? Given such a matrix, the problem is to find points P1, P2 up to Pn in Euclidean space such that the matrix entry Kij is equal to distance squared between 2 points Pi and Pj. So you are given a matrix K. So the question is to find out a good arrangement of points in Euclidean space in such a way that the matrix entry Kij is given by the distance squared of the points. This is the whole question. And remarks. This question is divided into 2 steps. First, conditions for such a existence of points in terms of matrix elements. And the second, construction of points. This question is a finite dimension, but the infinite dimensional generalization is parallel. Just a small remark. And such a matrix, such a good matrix is called Euclidean distance matrix. That is just a name for convenience. Okay. Now example. So Euclidean distance matrix satisfies this identity. Therefore, obviously, entries are all non-negative, and the diagonals are all 0. Moreover, this matrix is symmetric. So these two conditions are immediate consequence from the definition. Here is an example. Here are 3 points in the Euclidean plane. So number 1 and number 2 points, distance 1. Number 1, number 3, distance 1. And the number 2 and 3, square root 2. So we have such arrangement in Euclidean plane. Then the distance matrix is given by this 3 by 3 matrix D. Remember, we need to square of the distance. Therefore, distance matrix looks like this, 0, 1, 1, 1, 0, 2, 1, 2, 0, like this. Similarly, if you are considering 4 points in this way, the distance between the edges is 1 and 2, and the diagonal square root 5. Then the distance matrix looks like this. So very easy. But please remember that Euclidean distance is squared if you associate a distance matrix. Okay, now I said 2 simple questions, simple properties. So just consider this matrix D, 0, 1, 1, 1, 0, 9, 1, 9, 0. Okay, but this is not Euclidean distance matrix, because looking at this matrix, we need to set 3 points in Euclidean space. Distance between number 1, number 2 is 1. Number 1, number 3, 1. However, we cannot choose number 2, number 3 point with distance 3. Therefore, D is not Euclidean distance matrix. Okay. Now, natural question is the conditions for D to be a Euclidean distance matrix. So the answer was given by Schoenberg in 1930s. So here is a statement. So now let V be an index set, finite or infinite, and a real matrix D satisfying these 2 conditions. Symmetric and diagonal entries are all 0. Then the following 3 conditions are equivalent. This is the statement. First, D is an Euclidean distance matrix. This is our main target. And the first equivalent condition is that D is conditionally negative definite, C and D. Namely, the quadratic function FDF taking always non-positive values for every F on the hyperplane, orthogonal to 1. If we use the terminology QEC, then we may write QEC of D non-positive. Second equivalent condition is this. We take one element O from V as an origin and consider the matrix A given by this formula. Then the second equivalent condition is that this matrix A is positive definite. So positive definite to usual sense, this quadratic function associated to A is non-negative for all F. Here, the index set without the root O we selected at the beginning. So this is a theorem due to Schoenberg nearly 80 years ago. The proof is implication from 1 to 2 and 2 to 3 by direct computation because we need to show inequality. So the proof is by computation. Implication 3 from 3 to 1, condition 1, is we need some consideration. But A is positive definite matrix, so using A, we can introduce inner product and then we get Euclidean space, and we can find out suitable points. That is the story. I don't mention the real proof here, but maybe people who are interested in this kind of discussion, please refer to the old paper by Schoenberg. Now, we apply this idea to a graph. So, the graph Z is a set of vertices and edges. Okay, so we like to arrange the vertices in a Euclidean space in a good way, in the sense that the embedded point, if you consider the Euclidean distance squared, then it is exactly identical to the graph distance xy. So if this condition satisfied, this map phi is called quadratic embedding. Okay. By Schoenberg theorem, so we may rephrase this property in the following way. So the graph G admits a quadratic embedding if and only if the distance matrix is a Euclidean distance matrix. If and only if Euclidean, if and only if the distance matrix D is conditionally negative definite. So if and only if, by using my terminology QEC, quadratic embedding constant, this is the definition, you remember. So this condition is non-positive. So these are equivalent conditions. So G admits a quadratic embedding if and only if this QE constant is non-positive. Therefore, this QE constant is considered as a criteria for this quadratic embedding property. This is one of the motivation of my study. So here appears quadratic function associated to the distance matrix. Therefore, people are wondering it may be related to eigenvalues of D. Yes, it is. So I introduce distance spectrum of a graph G. That is defined to be the list of eigenvalues of D. D is a distance matrix, which is real symmetric matrix. Suppose the number of vertices is now n finite. Then we have n eigenvalues. They are all real numbers. So we arrange in the decreasing order. The largest eigenvalue, lambda 1, which is simple, known by Perron-Frobenius theory. And there is a second largest eigenvalue, lambda 2. Now here is a theorem. Our constant QEC is just between these two. Namely, QEC lies in the interval from lambda 1 to lambda 2. Lambda 2 to lambda 1, maybe. Okay. Actually, the proof is given by the minimax theorem because we know how to compute the eigenvalues of symmetric matrix. This is a knowledge from linear algebra. And comparing to our definition, we can immediately see that the lambda 2, here k equal to 2. Therefore, we need a codimension 1 subspaces here. But the QEC is taken over a particular hyperplane that is codimension 1. If you take all possible codimension 1 hyperplane, we get lambda 2. But here, particular 1. Therefore, lambda 2 is less than or equal QEC. This is the story. The right side, we need to apply Perron-Frobenius theory. And I don't go into the discussion today. So This theorem gives you our status of the QEC. QEC is not described by using distance spectra. It has something different information from distance spectra. So I think it is interesting to study further. This is the second motivation or background of my study. Okay, now I show you some examples. Here are some papers, and here is one paper is a joint paper with Indonesian colleague. Okay. Probably people are wondering what happens for a complete graph, path graph, cycles. These three are very basic series of graphs. Actually, not using QE constant, but codec embedding was discussed in earlier papers, because actually they are tracing back to Schoenberg, so it has some tradition. Okay, look at this picture. It's easy to understand the situation. Complete graph, for example, K4. There are 4 vertices. If you put K4 into 3-dimensional Euclidean space as a regular polyhedron, then each edge, the length of each edge is 1 in the Euclidean space, okay, right triangles. Then Euclidean distance 1, exactly 1 square is 1, which is graph distance. So this is codec embedding. If you consider Kn, you need a higher dimensional Euclidean space, but you can imagine what happens. P4 here, P4 is a path graph, but P4 can be embedded in a hypercube in 3 dimensions, like this. Remember, Euclidean distance of diagonal, namely endpoints. If hypercube is the right one, namely each length of edge is 1, then if you put 4 points like this, the distance between endpoints is square root of 3. It's obvious. What is a square? Square root of 3 squared is 3. 3 is exactly graph distance. Okay. So in this way, you can embed the path graph into Euclidean space, and the embedding is just quadratic embedding. Further, cycles are also, you can consider, you can create codec embedding. But later, I will show this by using eigenvalues. Okay, these are just starting examples. So my approach is not like this. My approach is computing QE constant of graph. If the constant is non-positive, we can consider, we have codec embedding. So we are interested in quantitative approach by using QEC. Okay, so now I like to compute QE constant, but there are not so many methods. So one typical method is based on the Lagrange multipliers, because QE constant is just a maximum value of quadratic function with certain condition, namely conditional maximum problem. So we introduce 2 new parameters, lambda and mu. These are called Lagrange multipliers. These are coefficients of conditions, respectively. So we consider this function and compute and find stationary points. There are many stationary points, actually. And among these stationary points, the maximum of this coordinate function can be found. That is a general story. In my case, it is convenient because the stationary point, we don't need to compute the value of f actually. This QEC is exactly the maximum of lambda appearing in this set. This is by somehow simple observation here, but this is very useful. So we compute the stationary point from the derivatives and look at this set and find out the maximum value of lambda. That gives you QE constant. So that is story. In this way, or other direct method, we could compute many examples. I show you some of them. So complete graph always QEC -1. Complete bipartite graphs like this. Here endpoint, endpoint. So, and complete tripartite graph of particular type. One endpoint here, then a value like this. So these are computed by direct method or by using Lagrange multipliers. And further graphs related to complete graph, I show you some examples. So Kn with deleted edges. So if you delete one edge, then QEC like this. If you delete two or more edges which are disjoint, the QE constant becomes 0. And deleting path of P3 or deleting some other complete graph, so we can compute such an examples explicitly. And also small graphs, and we tried to compute and collect all QE constant. So number of vertices 2, 3, and 4. Just this is not very important to look at very carefully, so I just show you. Here appears QE constant 0. And you see, these are all negative numbers. Now vertex number 5. Here again, QE constant negative, negative. Here appears 0 and negative, negative. Oh, positive appears here. This is misprint. And this is 0 and negative, 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 and so forth. And here appears positive and negative. Like this. There are 21 connected graphs on 5 vertices. And for more details, please refer to this paper. So now I'd like to mention the relation to distance spectra. I already mentioned that our QE constant is between lambda 1, lambda 2, largest distance eigenvalue and the second largest distance eigenvalue. And a graph G is called a transmission regular if the distance matrix has constant row sum. Row sum is just a sum of rows of the matrix. And if this value is independent of the choice of X, we call the graph is transmission regular. If transmission regular, we have this identity. Because the transmission regular, by definition, the constant one vector becomes an eigenvector, obviously. Therefore, delta is lambda 1. Then we can find out the second largest eigenvalue in the orthogonal complement of this constant one vector. But this is exactly the definition of QEC. Therefore, lambda 2 equal QEC G. This is the story. So if graph has some symmetry in this sense, then second largest eigenvalue is equal to QEC. But not always true. So by using this general theory for cycles, I could compute the QE constant explicitly. Obviously, cycles are transmission regular. It is very symmetric. Eigenvalue of distance matrix D are known or easy to compute because D is so-called circulant matrix. There is a canonical way to compute eigenvalues. Then these are results. Odd numbers and even number are different slightly, but anyway, eigenvalues are all known. And pick up the second largest eigenvalue, we get QEC. So this is the answer like this. Up to here, so if you are given a particular graph, there are some way to compute QEC, and it may be interesting to some extent, but it is not really a mathematical approach. One by one computation is not so creative, I think. So I need some systematic approach to this study. I started with some graph operations. Here is some, I show some simple ones: subgraph, star products, Cartesian products, and graph joins. These are certain graph operations. Okay. Now subgraph. This is quite convenient, so please remember here. A graph G is embedded in a bigger graph G tilde isometrically. Then we have this inequality. It's quite simple because this is the situation. Here is a small graph G and a large graph G tilde. As a subgraph G, we have no change of graph distance. Once you pick up two vertices in small graph G, we may count the length of the shortest path. That gives you the distance in G. But if you look at the bigger graph, there may be a shortcut. If there is a shortcut, the distance becomes shorter. But the condition isometrically means that there is no such shortcut. Then the distance matrix has this form. Submatrix, as a submatrix, D appears. Therefore, we have this inequality immediately. So, if QECG positive, QECG tilde positive, namely non-QE graph implies non-QE graph. Conversely, if G tilde is QE class, namely this value is negative, non-positive, then also QECG non-positive. So if G tilde is of QE class, so is G. So that is easy criteria. So as a corollary, we remember that every graph G, then QE constant is less than or equal -1. And here is another operation, star product. If you have two graphs and choosing root vertices or 1 or 2, and combining these two vertices, you get a big graph. That is called star product. In some literature, there are different names, but I call it star product. Then we have G1, G2 are of QE class, and star product is again QE class. In terms of QE constant, we have this estimate. So in a star product, G1 is a subgraph isometrically embedded in the star product. Therefore, we have this inequality. Therefore, there are two graphs, and so two QE constants, Q1, Q2. Then maximum Q1, Q2 is less than or equal QE constant. important part is bounded by certain constant Q12, and Q12 is given by this. So this is quite tough work, but it is, in some cases, it is useful. So I don't go into details, but the main information from here is we have some estimate of QEC for star product. Okay, now on the basic construction of graph, there is a method of Cartesian or direct product. So for direct product, so here G1 and D2 of QE class, namely QE constant non-positive, so is Cartesian product. But moreover, interesting is here, QE constant of direct product is always 0. And the graph join, if you are given two graphs, then we draw edges between these two graphs, as many as possible. So this is a graph join. In this case, the distance matrix is written by using adjacency matrix of graph G1 and G2. So it is it has a concise form. Therefore, in some case, we can compute explicitly the quadratic function, so we can get answer. Here is a formula. In that theorem, we assume that these are regular graphs. But anyway, we have such a formula for this. And applying this formula to concrete graphs, we have this kind of computation. Wheel, this is the graph join, cycle and one vertex. Complete split graph is a graph join of complete graph and complete empty graph, just endpoints. And friendship graph, like this. And for this, and we applied the theorem before to get QE constant, like this. Okay, some other structures, but it is omitted because of lack of time. Okay, now I am coming to the current project. So computation for such a graph suggests some more universal properties. At the beginning, I started just collecting examples of QE constant. But a one-by-one computation is not so creative, of course. Of course, you can enjoy the computation because that is just matrix analysis. And sometimes it is not so simple. Question is simple, but the solution, to get solution, sometimes difficult. But anyway, one-by-one computation is not so creative. And I also studied graph operations. But real interest may be here. This is also, some part is based on a joint paper with the Indonesian colleague. So I'd like to explain my question. First, I mentioned already, there are three sequences of basic graphs: complete graph, path graph, and cycle. I already shown the QE constant of complete graph, they are all -1. And cycles. I don't remember the real numbers, but cycles are computable, easy. But path, I didn't show any result of QE constant. Actually, it was difficult. So this is a distance matrix. And the question is very simple. Just considering the quadratic function associated to this distance matrix. And we find conditional maximum of this quadratic function. So question is simple. But I couldn't find the exact value. In this paper, we showed that these values are increasing and converging to -1/2. To show convergence, we need to estimate from below. I did it. And later, I showed with the scoring, inequalities are all strict. But finally, recently, my colleague, Polish colleague, private communication, these values are obtained finally. So it took some time to get exact value. So question is, looks simple, but sometimes computation is not so easy. Computation is not so easy actually. But anyway, we have a sequence of QE constant of paths. It looks like this. The QECP2 is -1, QECP3 -2/3, QECP4 -2 plus square root 2, and so forth. It increases strictly, converging to -1/2. And 0 appears here, and further positive numbers. So according to this scale, we propose a question to characterize graphs. The first attempt was done in this paper, a paper published in this year, but the result is 19. Excuse me, this is misprint. First of all, QE constant -1, if and only if it is complete graph. There are no other graphs having -1 QE constant. And between -1, -2/3, there is no graph. QE constant -2 or 2/3, the graph is P3 only. There is no other graph. Between -2/3 and -2 plus square root 2, there are some graphs. This is the complete graph star product with K2. K2 is just a segment, namely complete graph with one segment, like whisker. Or K3, K3. K3 is triangle. So joining triangle at one vertex, you get some graph. They are all. So in this way, we are thinking the graphs up to -1/2 is obtained in this way, or in a certain generalized way. We are conjecturing. But here, each segment, each interval, there are some graphs, but to determine all such graphs is probably difficult. Before that, maybe it is more realistic question to characterize graphs of which QE values is less than -1/2, namely here. So this is a problem. This is really, I think this is a realistic question to answer, to consider now. Also, next question, relation to second distance eigenvalue. If G is transmission regular, it is certain property of symmetric graph, then second largest eigenvalue of the distance matrix is equal to QEC. But the converse is not true. Here are some examples. Path graph P2, second largest eigenvalue equal QEC. But for P3, inequality, P4, equality, P5, inequality, P6, equality. So people are wondering, it is always. Yes, it is. In fact, we may prove that for odd n, strict inequality holds. For even n, equality holds. This was finally proven by the private communication of my colleague, because now we have a formula for QEC of Pn. So in fact, this is true. So you see, path graph is never transmission regular. If you consider the row sum, they are different each other. So there are some graphs which are not transmission linear, but equality holds. Then natural question is to characterize the graphs with this property. So this is a second project. Okay, now final project. Graph of non-QE class. So coming back the scale here. Okay, all the QE constant is more than -1. And up to -1/2, we are trying to classify according to the path graph. And between -1/2, 0, I have no idea at all. But positive case, namely the graphs which doesn't admit quadratic embedding in Euclidean space, those graphs we are hoping to have another approach. First, all graphs on vertex number less than or equal 4 are all QE. There are 21 connected graphs on 5 vertices, among which only 2 graphs are of non-QE. These are these 2 graphs. The first one QE constant 2/5. Second one something positive. Only 2. But here another observation already I mentioned. If G tilde has a subgraph embedded in G tilde isometrically, and if subgraph G is non-QE, then automatically G tilde is non-QE. So according to this observation, the problem 3 is to find the primary non-QE graphs. Primary, I mean non-QE graphs which don't contain any non-QE graphs as isometrically embedded subgraphs. For example, these 2 non-QE graphs, if you consider subgraph of these embedded in isometrical way, no more non-QE. So these are first example of primary graphs, primary non-QE graphs. So the question is find the primary non-QE graphs. So it might be quite interesting to study, but for the moment I have no idea. So I need your suggestion or advice. Okay, that's all for today. I mentioned QE constant and the quadratic embedding of graphs. It is related to graph theory, spectra, and analysis. So thank you very much for your patience. And I believe that QE constant is worthy of further study. Then I welcome any comments and proposals. Thank you very much. And it was a very nice opportunity for me to give a talk today. Thank you. That's all.
Thank you, Professor Obata, for nice talk. And let's check from the chat box. There is a response from Professor Kiki. Thank you for a nice presentation. And her question is there any specific property if the QEC equals 0 or QEC less than 0? Okay, please.
Okay. Thank you very much for the question. It is, of course, contained in my open question. So if the QE constant positive, we can say that the graph is not embedded in Euclidean space in a quadratic way. But the QE constant 0 has some special property, I imagine. So it is a really open question to characterize QE constant 0 graph. So maybe if you are interested, please try. We found that if the graph has a Cartesian direct product structure, always Q is constant to 0, but not always. There are other many examples. So for the moment, I have no proper answer to your question. Thank you.
Okay. We still okay because of we have limited time, and I think from the participants still have a question. Maybe can discuss later with Professor Obata by email.
Yes, and any comment and suggestion or proposal are welcome. This is my one of the favorite problems, so I hope to collaborate somehow. Thank you.
Okay, thank you, Professor Bata. Before we end this talk, let's give applause virtually for Professor Obata. Okay, thank you. And
thank you.
Then now I will give the time for the MC.
Okay. Thank you, Professor Nobuaki Obata and Dr. Alfi Zakia.
We are now going to the second speakers, Martianus Frederick Ezerman, PhD, from Nanyang Technological University, Singapore. The keynote speech will be moderated by Nathanael Karyanto, PhD, from Sungkyung Kwan University, Republic of Korea. Ladies and gentlemen, please welcome Martianus Frederick Ezerman, PhD, and Nathanael Karyanto, PhD. Time is yours.
Okay, good morning. Thank you very much for the introduction. So thank you for the privilege. The next speaker will be Dr. Ezerman. I hope I pronounced correctly. Martianus Frederick Ezerman. He spent undergraduate studies in Ateneo University in Manila, and then got PhD in 2011 from Nanyang Technological University in Singapore, and then since 2017 has been Senior Research Fellow at NTU, and the current research interest is in coding theory and theory of sequences. And today, Dr. Ezerman will present an interesting topic for many of us, and the theme is holographic sensings on images. Dr. Ezerman, the time is yours.
Very good morning. Sorry. Okay. I hope my audio and video feed is coming back okay. Very good morning, ladies and gentlemen, distinguished speakers, professors, students, colleagues. It's a privilege for me to share my research today with you. As introduced just now by the moderator, Dr. Karyanto, I'm going to share with you some results on holographic representations of data. For the simulations, I will concentrate more on images. So I'm very happy to join this international conference. Although my name sounds like a European name, I was born in East Java, in Madiun actually, and I grew up in East Java. I spent my educational years until senior high school in East Java. We move around quite a lot. My father works for the Indonesian government, so he was a forest ranger with the forestry department, so we move around a lot. A few years here, a few years there, always living near very nice forested areas and big rivers. So it's nice to have this chance of sharing with you today. And of course, as the Dean mentioned, it's my hope also to sometimes in the near future come and join you in person, maybe for the next iteration of this conference. So I will give a brief overview of the main ideas, the main development of tools that we have, and then applying it specifically on images. Before I mention to you, I direct you to the simulation softwares for you to try on your own. Okay. So first, I want to acknowledge the grant that support me in my research. So since 2014, actually, I've been supported by this grant, generously given by the university. My main research projects at NTU since around 2015 cover these three broad topics. As you can see, it's mostly in information theory, in coding theory, in cryptography. Have the privilege of working with a lot of wonderful colleagues from many many places in the world. So you can see the details there. And if you want to access the papers and the source codes of all the software implementation so far, you can go to my webpage. If the papers have been published and it's put under the paywall, I put there the accepted version, which is very close to the published one, as allowed by the copyright policy of the publisher. So we provide an almost identical version to the published one. You know, some of the numbering, some of the formattings will be different, but you can find them all there. So the results I want to share with you today come from this project. It's a holographic data representations. We are also generously supported by Singapore NRF from 2017 until just last year. I do a lot of other things as well with friends, colleagues. So you can see here the list. The one in red here, I put it in red because this is a cryptanalytic work. So usually I design codes and cryptographic systems, but occasionally I work with some colleagues doing works in attack. Okay. More recently, I started working on confidential computing with Huang Nguyen, who recently moved to Wollongong, and with Gilang, who is doing PhD in KU Leuven. So the reason why I'm putting this here is, of course, I'm open to collaborations. If some students wants to learn more about this, you're welcome. One of the mentoring I've been doing now is together with Professor Indah Emilia and Professor Diah Junia at UGM. I'm mentoring Pak Mustafa, working on his PhD thesis on modified Debrine sequence. So if you look at these things that I've been doing, it's broadly falling in the area of discrete mathematics, number theory, sprinkled with algebra, abstract, linear, multilinear. Specific to this project, holography, these are the 3 collaborators that are involved. Since the beginning of the project in 2016 until right now, we are at the moment we're not working hard on this program because COVID prevented us from traveling and continuing on this. But okay, so Prof. Ling San was my PhD supervisor a long time ago, and he's now my collaborator. Adamas is our lead programmer. He's also Indonesian. And Freddie is a Siam fellow, and he's a chair professor at Technion. He's also a visiting professor at NTU in our place. So he's an expert in robotics, signal processing, the geometry of signal processing. He's an expert in many things. Okay, so let me start with the initial idea of our project. Okay, so our work is translating the nice ideas that physicists have been looking into in terms of sensing and apply it to digital data. So in physics, a hologram is part of optics. So a hologram is produced by an optical sensing process. So if you have a scene, by the way, please excuse the drawing. The drawings are kind of horrible, but you know, I just want to put a little bit of personal touches into the lecture instead of just typing. Okay, so you have some scenes And then you use some optical sensing device to capture the scenes. Okay, how do you capture the scene? You use sensing waves, you reflect it on the scene, and then you capture the reflected sensing waves. Okay, so what is the output of this holographic sensing in physics? It's a recording of the scene. Of course, I'm using this term very loosely. What do you mean by recording? What do you mean by a scene? What do you mean by a sensing wave? My presentation here is deliberately vague because I don't know much of the physical details, but I understand the main ideas, and that's what we use, translating this to digital data. Okay, so without going into the details of the physics, here are some of the amazing aspects of hologram. So a hologram is visual. You can see it. It can be seen. Okay, so usually, even for people who don't know the details of the mathematics and the optics behind it, it is not very difficult. It's not very difficult to appreciate it. Okay, the second aspect here is very important for us. It's reduced dimension. So a typical scene is, of course, three-dimensional, but the hologram is a two-dimensional plate. Okay, now this two-dimensional plate produces a representation of a three-dimensional scene. Okay, and if once shine rays of light on this plate, two-dimensional plate, then it makes the 3D scene appears again, as if by magic. Okay, so this is the most magical properties that we want to capture. And we want to translate this idea into representations of stochastic digital data. So the most magical property is if we have a hologram plate here. This is a two-dimensional representations of our 3D objects or scenes. And if you break this hologram plate, okay, let's say here I break it into these portions, and then I shine lights only on a randomly chosen part. Let's say we shine light on this portion only. Okay. Without having the information from all the other portion, just by taking these portions and shining lights on it, you recover the entire scene. And here's the key word, here is the entire. Not just some portion of the scene, but the entire scene. Of course, if you have only some portion, then there is a less fidelity. You have less faithful representations of the scene. Okay, so your hologram may appear weaker, it may appear blurry, it appears less stable, but it still represents the entire scene. Now, the quality of recovery depends on the ratio of the parts available. It doesn't depend on which part you select, because here, you see, you can just use a randomly chosen part. So for example, if you take, instead of this portion I highlighted here, I put different color. I take this one here on the right middle side here, near the right end of the rectangle. If I do the same thing here, you also recover the entire scene. If you combine now two portions, you also recover the entire scene, but now with better fidelity, sharper image, more stable. And as more and more portion are being used in the recovery, your recovered scene becomes sharper and sharper, higher in fidelity. Less error if you want to look at it from perspective of error control. So Freddie Brookstein and two of his colleagues work in Bell Laboratories some 20 years ago, I think 20 plus years ago. They come up with an idea of using holographic representations for digital watermarking. Okay, and so when Freddie came to NTU in 2016, he explained this thing to us when we were just having coffee in the afternoon, you know. And he said that, well, he had some ideas way back in the 1990s, end of 1990s. And then he said that it's a nice idea, but he didn't know how to extend it. And I work mostly on cryptography. And when I heard this idea, I thought, like, this sounds like secret sharing. The idea of secret sharing in cryptography. So then we were just combining ideas from two very unlikely sources. I mean, you don't usually combine image sensing. You don't combine signal processing with cryptographic key reconstructions. But it turns out that there are some tools, that some ideas that we can combine from both sides. So if you're interested to learn more about the background and motivations of the transition from holographic representations of scenes in optics in physics to the idea of using it for stochastic data, you can watch this video. It's Freddie Brookstein's lecture. He explained more about the background and motivation. So these are some of the main takeaway points from there. So it was invented by Denis Gabor in 1947. It got him the Nobel Prize in 1971. You have a lot of applications, you know, in art, microscopy sensors, security, optical data storage. These are all using using optical hologram. Okay, the core idea behind digital watermarking. So let's say you want to rent a video. Okay, you want to rent a video. There is a mechanism from the owner of the video that after 72 hours, I mean, after 3 days or after some days, the video will not be playable anymore. And it will also prevent you from sharing it illegally. You know, you cannot just pass it to your friend and say, okay, now you play this, you can play this on your machine, something like that. So images, videos, you can put watermarking, and even if a portion only of the video is shared, the owner, the rightful owner of the copyright can say, no, you don't have right to share that. Okay, so what we want to do here for this project is we revisit the idea of optical holographic sensing and representations now to formulate distributed digital data acquisitions. So you want, right, okay, nowadays when you deal with data transfer over the internet, over any channels, right, you send them as packets. You don't send the image as a whole image like that. It is broken down to packets of representations so that it can go through the channels in multi-input, multi-output ways. And at the end, the recipients of your message should be able to recover it. So if you send images, it should be recoverable. If you send videos, it must be recoverable. Any form of digital data nowadays often goes through the channels in packets, in distributed packets, and that's why we think that this is something very, very useful there. Okay. So now we want to translate the desirable properties from optical holographic to data representations. We want fidelity in recovery. So the recovered value should approximate the actual value up to some threshold. So we want to minimize the error when you recover the thing. Okay, and of course we want it to be efficient enough for it to be practical. And depending on the domain, we want our data representations to have some good performance metric. But this is specific to applications. Let me try to explain it a bit. When you send audio, your measure of goodness is different than when you send image. So what does it mean to have a good recovery when you play audio or when you watch movies? These are different. So I mean, we want to have a measure specific to application domain. Now, there are other models than this holographic, successive refinement of information. This was developed by Eckwitz and Koffer in 1991. Tom Koffer was a good friend of Freddie Brookstein's PhD supervisor, so they have a lot of discussions way back when he was in Stanford as a PhD student many years ago. Then perhaps you have heard about compress or compressive sensing. This is used a lot in video and image sensing or sensors these days. It was pioneered by Donoho, Romberg, and Tao. This Tao here is Terry Tao, Terence Tao, field medalist. So it has produced impressive tools. You have a lot of astonishing progress here. And in around 2001, Vivek Goyal come up with this multiple description coding. This is essentially a coding mechanism that is designed so that you get a good sequential recovery. So in Goyal's work, what he proposes is the following: not all information in an image is equally important. So there are parts which are more important and there are parts which are less important. So what you do when you are processing image is you send the most important parts first, make sure that they are recovered properly, and then you put on all the details later. So the difference between multiple description coding and holographic is that in multiple description coding, some portions are more important than others. In our model, we don't really care about the importance. Okay. We treat them as equally important. So these are the objective of holographic sensing from a high level thinking. Okay, the sensing process must generate and distribute multiple description of information in packets. Why in packets? If I have explained, when you process this and send it over the channel, the internet, for example, is a very wide curve if you model it as a graph, right? So if I'm sending an image from here, like right now I'm talking, the video is sent through multiple channels, and therefore the information feed is done in packets. So the packets, so the first one, we want progressive recovery. As I mentioned, the more packets you have, the more portions of the hologram plates you have, you get better and better recovery. And the recovery must be progressive. For example, if you have one packet, and then you have two packets, and then you have three packets, any three packets must be better than any two packets. Any 5 packets combined must be better than any 4 packets combined. And there the keyword is any packets, any set of packets. You don't say that packet number 1 is more important than packet number 2, is more important than packet number 3. Every packet is as important as the others, more or less. You see, that brings me to the second point. The packets are designed to have as equal importance as possible. So if you break down your information or your image into 8 packets, and then you take any 2 packets, for example, packet 1 and 2 or packet 1 and 7, the recovery of these 2, let's say you compare the recovery between packet 1 and 2 and packet 1 and 7, they should more or less be the same. So we don't really care about which packet arrive and can be used. We just care about how many. So as more and more packets arrive, you should get better recovery. So then come the most important question. So how do you make the representation then? So our idea is really following the optics processing. There you have three-dimensional scenes, and then you project it into two-dimensional plate. Here, if we have a big image, okay, let's say then we break it down into 64 dimensions. Okay, so the entry comes in a vector of length 64. Then we are going to project it. We design projection operators. Okay, so the object of interest, so the stochastic data, be it audio, video, text, anything, you represent it in high dimensional vector forms. And then this is the most important part. We design the projection operators such that the output of these projection operators, you have lower dimensional vectors. For example, from 64, now we have as an output vectors of length 8, for example. So it's 1/8 of the original. But then we need to do this holographic sense, this projection operator design to ensure that the objectives are met. What are the objectives? Well, we want progressive recovery and we want smoothness. So these are the two governing principles in the design. So here's the general framework. If you are interested to read the details, the mathematics of the process, it's in this paper. In my webpage, you can download the accepted version. So not this version, but the accepted version. The content is identical. So here in the general framework, we don't really care what type of data it is. We just care that this is a stochastic data. Okay, and here, this paper is published just this year, earlier this year. This one is we are applying it on image. Okay, so we implement the general idea of holographic sensing on natural images. And our strategy is we look at it as bit allocation problems. So this appears in this the flagship journal of Society of Industrial and Applied Mathematics for imaging sciences. This one in my webpage, you can download the actual published version because we can distribute it openly. So let me give you a simplified comparison, okay, on Sketch. So here's what happened. If you use a hierarchical or multi-resolution approach, for example, this is the one that comes from successive refinement, okay, or from multiple description coding. What happened is this. First, you send the most important portion of the data. How do you decide which portion is most important or not? Well, that comes from some spectral analysis, actually, from the eigenvalues of the data representations. We'll touch more about it in a while. And the next packet will fill up more details. And packet 3, even more details, all the way until you have your entire packets, all of the details are there. But here it is hierarchical, meaning this packet 1 is more important than packet 2. It's more important than packet 3. The problem sometimes, so the difficulty with this kind of multi-resolution recovery is that, for example, you have packet 1 and packet 2. Packet 3 you have. But then packet 4 does not arrive. For whatever reason, in the channel it get erased, it got lost somewhere. Packet 4 doesn't arrive. What happened? Packet 5, packet 6 until packet n will not be recoverable. So before you can include packet n+1 into the process, you must have packet 1 up to packet n. So if for some reason packet 1 doesn't appear, then that's it. You don't get anything. Of course, it is very rare that the most important packet doesn't appear, because you usually put a better error correcting or erasure correcting system on it, or encoding decoding system on it, because this is the most important, right? So this is how a hierarchical image recovery works. Now, what about holographic? We don't care about the hierarchy here. So for holographic, any one packet, it doesn't have to be packet 1. Any one packet will give you a rough sketch. Any 2 packets will put more details. Any 3 packets will put more details. And here, when we mean any, it's really any. We don't really care which portion. And as you have more and more packets you can reconstruct, then your image become better, sharper, less error. And when you have all the packets, it should be okay. You recover the whole thing. Okay, so the main idea is when we do holographic sensing, the order of availability is irrelevant and recovery must be uniform. So we don't care about the order of arrival, because some packets may take longer depending on the channel situation. Okay. Think of it like you're traveling from Jember to Surabaya. There are many possible routes that you can choose. And sometimes if you take one route, you come faster than if you take the other routes. And sometimes there are some issue with the route, you cannot pass. Okay, so the packet doesn't arrive. But here we don't really care which one. Whichever comes first, we process. Okay, so what are the tools? You might be thinking, well, what kind of mathematics are being used? All the mathematics are simple. So I'm not saying they are easy. I'm just saying they're simple. Simple meanings that they were taught in a good undergraduate program. Okay. So we use, from linear algebra, we use eigenvalues and eigenvectors and eigendecompositions. From statistics, we use autocovariance matrix and SVDs, singular value decompositions. Nothing very, very powerful, or we don't really need to build new grand tools in mathematics. This is just choosing the right tools from all these diverse areas is important. We do have some multivariate calculus, but it's just optimization by a Lagrange multiplier. And the nice thing is at the end, we have a closed formula of the error. Okay. And then simple algorithms for bit allocations. So I deliberately did not when preparing the slide, I decided not to put all the mathematical details. Because I want to invite the students to have a look, and here I'm trying to tell you, none of the tools that we use in those 2 papers requires advanced graduate level mathematics. Okay, and that's what really fun about this project, because at the beginning we thought that the right tool will need to come from manifolds. It will need to come from algebraic geometry. It will need to come from something very sophisticated. And it turns out during the course of our research that yes, that very powerful tools will work, but not as good as the simple tools. So that is something that we explain also. If you look at this paper in section 7, we explain why the more powerful tools actually perform worse than the simple tool that we use here. So okay, so we work on natural images, right? So this picture here on the upper left part, I took this picture in Singapore Botanic Garden. Actually, I was having picnic with my family. There, the Botanic Garden is not very far from where we live, and suddenly my son saw this big monitor lizard on a tree. So yeah, I took a picture of this. This picture on the upper right is taken by Fardin Oyan. I used this picture with permission from him. This one won some photography award. I forgot the details, but Fardin Oyan is from Sri Lanka. Sorry. This one on the left lower part is a photo of Merlion. It's a free image, stock image. Sorry. This one, the picture of an old lady here is taken by Indonesian photographer Rarindra Prakarsa. Maybe you've heard his name. I'm a fan of his picture, of his photography. Actually, he took a lot of nice photos. Also used with his permission. So if you look at the software suite that we put in GitHub, you will see a lot more images that we use for this project. I'm putting them here just to show you that we don't use painting, sketches, although the mechanism can be applied on them. The reason why we want natural images is because natural images has more variance. Okay, so when you look at their first and second order statistics, they vary a lot more than not natural images. So here's the outlines of the main step. These are the most what you call it, technical part of my slides actually. So you have an image, you break them down into vector representations of let's say length 64, and the representations there is just the pixel values. Okay. Then what happened? You put them as vectors and vectors and vectors and vectors, and then essentially that builds you a code book. And from that code book, okay, so you index the vector representation v1, v2, and so on until, so this omega is the index set. And then now you compute the autocovariance matrix. So the X here is that long vector representations. You multiply it with the transpose, and then you just average it. And that's your autocovariant matrix. And then you use SVD to turn this into psi delta psi transpose. Okay. And then this psi and delta matrix, sorry, psi and lambda matrices will be crucial when you design the projection operators. Okay, then we determine the projection operators that minimize the mean squared error. So this is what we use as a measure of goodness. When the mean squared error is lower, that means the recovery is better. And then how do you measure the smoothness of the recovery? Well, you just take a look at the expected mean square error for any L packets. So we have N packets. As I said, you know, any one packet, any two packets, any three packets should give you the more or less the same quality. So this is how we measure it. So L is a value between 1 and N. So L tells you how many packets you have. And then you just measure the expected of the mean square error when you have any L packets. And this is now the formula. You know, it may look a bit complicated, but it's actually super simple. It's just basic linear algebra. Nothing really fancy there. So here's the lambda matrix. So here we look at 49 different natural images, and then we look at the lambda matrix value. You can see here, that's the lambda matrix value. Okay. So we collect all of these images, and then we look at these lambda values. The bold black one here is the mean. Okay, and as you can see, there is a variance here. There's quite some variance. So the vertical axis here is in logarithmic scale. Otherwise, the picture will be too wide. So we put it on logarithmic scale. So what is the message here? The message here is there is high eigenvalues here for the first few locations in the image representations. Okay. We explained the interpretation of this in details in the second paper. Okay, so the model and recovery procedure in the most general situations is in section 2 of the paper, of the second paper. So I'm referring to this paper. Okay. For those of you who wants to go into the details, this is just some guidelines on how you read them. We explain how to get the lambda matrix. The channel is assumed to be noisy, so we can handle noise. The recovered estimate is given in that equations and how the mean square error is defined. Okay, the sensing design come in three modes. We explain the reason why we chose the modes and everything is there. The rest of the papers are implementation of analysis, actual data sets. So overall, our proposal has some very nice properties. It adjusts well to changes of parameters. So for example, the noise in the channel suddenly spike up. Can you handle it? Yes. What happens if you cannot send, instead of sending, let's say, 16 packets, you're now constrained to send only 8 packets. Can you adjust? Yes, no problem. Okay, and in fact, we did further statistical analysis, and then we found out that you don't need to use the individual first and second order statistics of each image. You can just choose the average, and your recovery will be very, very close to the quality that you get if you use the actual image statistic. Why do we need to do that? Because, of course, the data here we get from specifically chosen images, right? What happens if you want to recover an image? You want to send, and then recover the image whose statistic you don't know. Of course, then you can just use this mean lambda value here. Okay, and progressive smoothness, you can see it from the statistical analysis. So here is an example. So I use this picture here as my target picture. Okay, this will be dragon. Where is dragon? Here. Then we have this. Okay. Now I'm sending it using, so I break it into factor of length 64. The noise level, the sigma noise level is here. So sigma n squared, this gives you the noise level. And my vector representations after the projection operator is 8-dimensional. And we have 8 packets. So this is a randomized recovery. So if I take one random packets and I recover it, I get this image on the left upper corner. If I take 2, I get this. If I take 8 all, I get this. And you can see there's a progressive refinement. Okay, here you see the progressive refinement. As more and more packets you have, you recover. And then you might be asking, well, C and D, C is more noisy than D. Yes, of course, because we handle noise here. So then you can further do refinement on how to handle this noise. So what happens if I increase the noise? As you can see here, the noise square of the noise is 0.64. This is the standard deviation of the noise, right? Sigma n. So then here I use a higher noise level. What happened? As you can see, the upper left part here is more blurry than this one. Okay, as you have a higher noise level, but this is your output will be more noisy. It's noisier, but then you see, you still get the progressive recovery. We actually, in the simulation, we push the noise level up to 2, 4, and so on. You can always handle it. The system handle it well. And here's a control image. This is actually a photo of my son when he was, I think, 4 or 5 years old. We were playing in Sentosa Island here. So this is a control image, meaning I use the mean statistic of the lambda value to recover this. And you can see the same property happens. And this graph here tells you the smoothness of the recovery. You see here the average MSE plot for various images. So L here from left to right, you get more and more packets. As you get more and more packets, the error drops. Okay. And then the variance here tells you that as more and more packets arrive, the variance of the recovered results becomes smaller and smaller and smaller. At some point, the smoothness is very obvious, meaning regardless of which packet you get, at about half the number of total packets, the quality is exactly the same. Okay, and here is the proof of concept software. It's out in the open for those of you who are into signal processing, so those of you with more computer science interest. Adamas put his entire source code for this project in his GitHub. There is instructions on how to run the codes and everything. This one was written in Python 2.7. So if you use the latest version of Python 3, maybe you need to change the code a little bit. But I trust that if you're used to doing Python programming, you can install Python 2.7 and run on it. Our implementation there is basic, okay, because we just want to show that, okay, our system works, our entire setup of the sensing, representations, and recovery, they work as claimed. We don't optimize it. We don't optimize it for speed. We don't optimize it for memory, although it's already very, very good, meaning practical. You can run it on a normal, on your normal PC, and it will not cause any problem. Okay, so I end here. I'll be happy to entertain questions. Thank you very much.
Okay, thank you very much, Dr. Eizaman, for the exciting presentation. Are there any questions from the audience? Oh, let's first give applause to Dr. Eizaman.
Thank you.
Thank you very much.
Thank you.
Are there any questions from the audience? Perhaps you can write a chat. You can write in the chat room and then send in the Zoom chat room. We have time. So meanwhile, maybe I can ask a very simple question, because this is not my field. I just know a little bit about this image processing and then this cryptography. So suppose if you you want to give an advice to undergraduate students majoring in mathematics, what courses that one needs to take in order to conduct research in this area? I think maybe it's number theory, but maybe you can elaborate further. Dr. Eizaman, please.
Well, I guess I can only give very broad pointers instead of advice. If you look at, sorry, you see, I work in quite a few topics at the same time. When did I start getting interested in doing research? I suppose it was in my third year as an undergraduate student. In the 5th semester in Ateneo, we have this wonderful seminar class. At Ateneo, not every undergraduate students are required to write thesis. only a few who are invited by the department to write thesis, eventually write thesis. In fact, in my batch, I think I was the only one who ended up completing a thesis. So it's not mandatory to write a thesis as an undergraduate student, but that seminar in the 5th semester, what happened is the department organized weekly seminars. They invite professors from different areas to come and give a talk about their research, to give a talk about their interests, and to sort of mention all the open problems that they think available within the reach of an undergraduate student. And at NTU, actually, I had the privilege of supervising not just undergraduate research, but also high school research. So in Singapore, there is this program by the Ministry of Education. They invite all the mathematically inclined high school students to form a group of 3 or 4, and then pairing it up with researchers like myself. So we give presentations of what problems we think they can do, and then they are free to apply. So as an undergrad student, the first thing I would say, if you want to go into research, is to broaden your foundations. It's very important to know, at least to get exposed to a lot of fields of mathematics. And I'm naturally a busybody. I ask people what research they're doing. I tell them what research questions I'm working on, and because of that, I work with a lot of people. And then the most interesting aspects is sometimes just by telling them what you're interested in and asking them what they are interested in, what they're working on, a new collaboration comes up. Like this particular project holography, I mean, Freddie Brookstein comes from a very different background than us. So Prof. Lingson, by training, is an algebraist. And he did a lot of algebraic geometry. I come from more of number theoretic, discrete mathematics background. Freddie Brookstein is an engineer. Actually, he's by training, his PhD is in electrical engineering. And then he became professor of computer science. So we work on a very different areas. And I think it's important to be open to as you're forming up your foundation as an undergraduate student, it's very important to broaden your interest. Let's say you're not very interested in discrete mathematics. It will worth your while and energy to come and listen to talks in areas that you don't really like, or you don't feel immediate connection at the beginning. If you want to go into cryptography and coding theory, so cryptography and coding theory, they use almost the same set of tools, although there are different purposes. In cryptography, the purpose is you want to represent information in such a way that it can handle erasure, it can handle error, and then you can recover the information that you need depending on the dynamic of the channel. What do I mean by that? When you store information, you have a very large data, you want to store them. You need to be strategic about storing them. You don't store multiple copies of the same huge data. You want to distribute them in such a way that you can recover them. Let's say, for example, one of your server went down. One of your data center went down. How do you make sure that there is no disruption of service? That's very important. When you send channels over wireless connection, it's different than when you use local area network, which is wired inside your organizations or inside your lab, for example. So the concern of coding theory is fidelity. How do you recover? How do you maintain the integrity of your informations? In cryptography, the interest is different. In cryptography, you want to make sure that parties or people or machines that supposed to work together can work together. And their communications, the exchanges are protected from adversary, from people or computers that should not have access to the communications. And sometimes you also, in cryptography, you want to make sure that a particular data is not changed. So for example, if I'm connecting to my bank by internet banking, and I tell the bank, please transfer 10 million rupiahs to Adamas. Nobody can change that to please transfer 100 million rupiahs to Adamas. That will be very dangerous. Okay, if we have something like that, then it will be very, very dangerous. So you want to maintain. So for example, you have a very important certificate. You want to send a software update. Before your client download it, the client computer need to make sure that this software is not changed. Otherwise, it can get very, very dangerous for your system. So the tools, the mathematical tools come from where? Well, it comes from number theory, algebra, discrete math, with a bit of statistic. But you also need to know how to code. You need to think like a computer scientist sometimes, because the mathematics are implemented in software or hardware. So it's nice to have collaboration like this. Prasanna, Rafi, and Shivam Bashin, they are experts in embedded system and hardware. So to sum it up, number one, broaden your foundations. Number two, be interested in what other people are doing. You know, attend lecture, attend seminar. And three, be equipped with multiple expertise. When I was an undergraduate student, as a mathematics student, you're not given a serious programming course. Then later on, I need to do a lot of programming, so I learn on my own. So I hope that at least give you an idea of what preparation will be ideal if you want to be a researcher in the future for students. Thank you.
Okay, thank you, Dr. Ezeman, for the insightful advice. I guess that will be useful for undergraduate students who are interested to become researchers in mathematics, taking a lot of classes in number theory and discrete mathematics, statistics, and also programming and so on. And also for faculty members, you can also advise your students to involve in this kind of activities. Are there any other questions? It seems that our colleagues are quite shy, and the time is also almost come to the end.
Sorry.
Yeah, the session will start in 2 minutes, so I guess we stop here. So I give you applause again. Thank you very much.
Thank you.
Dr.
Thank you
Ezeman,
very much for your
presentation.
attention. Thank you.
And I leave it to I return it back to the Master of Ceremonies.
Thank you.
Thank you.
Thank you, Martianus Frederick Ezeman, PhD, and Nathanael Karyanto, PhD.
We are now continuing to keynote speech Fernando Marmolejo Ramos, PhD, from University of South Australia, Australia. The keynote speech will be moderated by Dr. Alfian Futuhul Hadi from University of Jember, Indonesia. Ladies and gentlemen, we are sorry that Fernando Marmolejo Ramos, PhD, could not attend in person today because he is at another duty at the same time. Instead, he already sent a video for his speech. Without further ado, please welcome Dr. Alfian Futuhul Hadi to moderate this session.
Now is the time for us to put into our attention to what Professor Fernando Ramos from South Australian University. This is sent us video presentation. But firstly, I will introduce Professor Fernando Ramos. He is a PhD from Adelaide University at 2011 and Master Applied of Science from University of Ballarat, Australia. Now he is a visiting researcher fellow at School of Philosophy, the University Adelaide in South of Australia. Another position is he is also this full-timer is on fellowship research fellow on Adelaide South Australia University, research fellow at University of South Australia. Major research he is doing is on psychological quantitative method, I think, sometimes related to statistics and then what he calls as psychometrics. His research interests in the research methods and statistics are also on robust method, statistical cognitions, and other fields. His presentation today is entitled with open science research practices for the era of big data or reducing questionable research and measurement practices. I think this is an interesting field of research, and I think we will enjoy this video presentation. Is about Howard. So I give a time for the operator or co-host, which is on the duty to start the video. Then audience and all participants can put the question on that box. So I think we have to save the time because it is an hour video presentation. Thank you.
Thank you for inviting me to this conference, the International Conference on Mathematics, Geometry, Statistics and Computation, organized by the University of, I had the name just here before, Universitas Jember in Jalan Kalimantan. My pronunciation was not the best, but I tried. And Indonesia. Thank you very much for this invitation, and I'm very pleased to be able to deliver the content of my talk to you today. And I really apologize for not being able to be live in your local time, but it didn't match my schedule, and I had to attend something unexpectedly. So I really apologize for that. But I thank the organizers for this event and for having everything well sorted and in place. Today's activity is going to cover different things, different topics. So the opening session by the Profile of Mathematics Department. Then we'll have the talk by the chairman of the IC-MaGeStiC conference. Then we have the rector of the university, then Professor Nobuaki Obata, then Martianus Frederick Eserman, then my talk, which, like I said before, I cannot deliver in person and live because I have to attend an unexpected situation. And then after my video clip, you have the chance to see Professor Marco Valkonen. That's in the morning time. right up to 1 p.m. local time, Indonesia time. And then in the afternoon, you have different talks, different rooms about graph and algebra, modeling and analysis, statistics 1, statistics 2. I'm looking forward to, I would like to see the talk by Professor IC-MaGeStiC, but I'm very keen on seeing the other talks. So if I have the chance to have access to those video clips, please send them my way, as I'll be happy to provide feedback and brainstorm ideas in that regard. So I guess you can have my video at the moment. Yeah, I think you can see it, but I'll be turning it off and on every now and then so you can see the slides completely, so I don't provide intrusive views for you while you enjoy this talk. So my talk will be about open science research practices for the era of big data, and I put the subtitle, All Reducing Questionable Research and Measurement Practices. And I emphasize measurement because it's something that is a hot topic these days. I thank the laboratory I'm part of, which is this one, the Center for Change and Complexity in Learning at the University of South Australia. And I'm also part of a laboratory in Chile, which is the laboratory, it would translate something like Interdisciplinary Laboratory of Social Statistics. And I have some collaborators there with whom we are doing some very cool research on measurement. All right, so this is the content of my talk. We're going to cover things in open science, which is a big thing these days. I'll talk about the pre-registration initiative. We'll cover things about reproducibility, replicability, and robustness. Then we have approaches to enhancing the 3 R's, which are these ones, through an approach that I really favor a lot, which is called the many lab studies. Now, you might think that this one is focusing only for those doing experimental studies or collecting data, like in the health fields, psychology, environmental sciences, and so on. But actually, this approach can be extended and is fully applicable to research in statistical sciences. And I'll be talking about that later on. Bottom line, or in a nutshell, basically, in statistics, it's very typical that people or researchers tend to run simulations on a computer in a university, but it would be nice to be able to replicate the same codes, the same simulation in different laboratories. Why? First, you'll get access to more simulated data. So if you collected 10,000 runs in your laboratory, the other person 10,000 in his computer, the other person 10,000 in her computer, then you have a representative sample. The other thing is that when it comes to the modeling of data, you can enter laboratory as a covariate or as a random effect in the modeling to see whether data coming from different places has an effect on the outcome. And also, you might even ask one of the collaborators to simulate data using a different random generator. So that's interesting to cover those things because you might see if the random generator is actually affecting the results. And the last topic would be about measurement, measurement, and measurement. That's a topic that I really favor a lot and is essential in any science that is aiming to take some data and measure something about a construct or a topic of interest. Okay, and I'll be referring to a field called learning analytics, which is a field that is also called educational data mining. And the reason is that I have some issue with the way they define learning, as it is actually better defined from psychometrics. Then I'll be talking about better statistical techniques and an approach that is called the multiverse analysis. And then you'll see what I'm referring to when I get to that point. Okay, so the first thing is open science. Bottom line, open science is defined as the movement to make scientific research, including publications, data, physical samples, and software, and its dissemination accessible to all levels of an inquiring society, amateur or professional. The ultimate goal is to increase transparency in research. That's the main goal. So Open Science covers different topics such as open source software, open hardware, open evaluation, open science infrastructures, open educational resources, openness to diversity of knowledge, open engagements of social actors, open access publication, open data. Okay, and these two in particular, let me just move this camera somewhere else. Let me see if I can do that. It seems like I cannot, but let me just turn it off for a little while. No, it seems like I cannot. But this one, it says openness to all scholarly knowledge and inquiry. That's what it says here. I apologize for the video not allowing you to see what they are. I'm trying to move the video, but I cannot. Well, it's not a big deal anyway. Now, this one. An example of what Open Science does and looks like. So I'm referring to some news that appeared in 14 December 2020, and the title of this was in BBC News. The title was "Is There Life Floating in the Clouds of Venus?" So they refer to some study, they found something, and this is the actual paper reporting the finding. Was published in Nature Astronomy. Alright, so we have different co-authors, we have the abstract, and so on. But the reason I'm showing you this is because towards the end they have this data availability, they provide access to the data, and code availability. See? So you have access to both things. And then I saw on the internet, on the website where the news was being shown, they interviewed the professor who was the lead researcher, which is, seems like I cannot go back. Okay. He said, through my whole career, I have been interested in the search for life elsewhere in the universe. So I'm just blown away that this is even possible, Professor Graves said. Now, this is the part that is perhaps the most important. But yes, we are genuinely encouraging other people to tell us what we might have missed. Our paper and data are open access. This is how science works. I think there is no better way to put it. And the paper also has a section on author contribution, so you can see what every single author did in the paper. Here's another example. It's a paper called Improving Data Access Democratizes and Diversifies Science. This was published in the journal PNAS in 2021, I guess. Now, the interesting part is that this one, what it's doing is showing the following. The analysis show that improved access to data had a substantial and positive effect on the quantity and quality of Landsat-enabled science. Improved data or access also democratizes science by disproportionately helping scientists from the developing world and lower-ranked institutions to publish using Landsat data. Then again, it's about the importance of sharing data. You see, what this is showing, and you see the map here, is that countries that didn't have access to some technologies and therefore the data, they can now analyze such data sets because it's being shared. And they can find new things because it's like more eyes looking into the same topic. It's not the usual eyes, which is the US and Europe because they have the facilities, or Australia, but it's now other different places having access to data sets. So you can see the black dots represent the locations of the new Landsat authors. You see, post 95 when they made the data available. You see, this is the gray dots are the locations of the authors using the Landsat by 1995. Okay. So mostly concentrated in some places in the US, some places in Europe, but now other countries have access to that data. You can see, for example, it's very interesting to see in the African countries, some of the Asia region have more access to that data. This is an example from neuroscience. It's from the journal called Brain Structure and Function. Quantification of neurons in the hippocampal formation of chimpanzees, comparison to rhesus monkey and humans. Then again, we don't care about the topic itself. We care about seeing this. Authors put in a correction a few weeks after. But then again, what matters is that journals are now showing the author contributions, just to state very clearly what every person did in the paper. And that's very important because we can say that in classic papers, this you didn't come across this kind of text in the publication. It just puts the title, name of the authors, acknowledgements, perhaps acknowledging the funding source, but nothing about the authors, what each person did. That's like a new thing, but it's very important. And then again, in this paper, they have a section called availability of data and material, and then you can access all the data here. Now, this paper should be of interest to all of us. And actually, seeing this paper reminds me of another paper that is very, very interesting. Actually, let me see if I can overpost screens. Yes, I can. There is a paper that came out in Science just recently. Let me see if I can find it. The role of statistics in AI. Yes, this paper was published just recently. So, okay. So going back to this paper, transparency and reproducibility in artificial intelligence. This issue is precisely what we're talking about. It has to do with open science, but now they're making the call for research in AI, which implies machine learning, which implies statistics as we know it, to make such data sets available, to make code available so that researchers can make progress. So this paper is interesting because if you notice that one of the authors is this guy, John Ioannidis. He's one of the guys who started talking about the replication crisis in the health sciences. Where is the mouse now? Right here. So he was the one talking about the replication crisis. Oh, sorry, the slide just went forward. Let me see if I can go back. Maybe yes, maybe no. No, I cannot. Well, doesn't matter. So well, in that paper, basically we have Ioannidis, we have Tip Shirani, and we have big names in statistics, as we know, statistical learning, making this call all together about AI being more open, AI and machine learning. Now this is an example from computational biology. By the way, this is the paper I was going to show you just briefly that talks about something that might be of your interest. Let me see if I can show you quickly over and post on the screen. If you have the chance, try to read this paper. It's in a journal called Advances in Data Analytics and Classification. Maybe you cannot see it, perhaps. Now maybe you cannot see it. Yeah, maybe now I can see it. Yeah, I guess you're seeing it. It's called, the journal is called Advances in Data Analysis and Classification. Came out just recently, and the paper is called, Is There a Role for Statistics in Artificial Intelligence? I highly recommend it. Highly recommend it. It then again has to do with how statistics relates to machine learning and therefore AI. And all of this has to do with open science. Okay, this is from a paper that is called 10 Simple Rules for Reproducible Computational Research in the journal PLOS Computational Biology. Highly recommended too because it provides you some guidelines as to how to embrace reproducible science. This is from a paper called The Likelihood of Null Effects of Large NHLBI Clinical Trials Has Increased Over Time in PLOS One, published in 2015. But it's interesting to see how after the year 2000, when the registration of primary outcomes was required on clinical trials, you can see that the number of benefits, you see, reduced substantially. You see? Now we have a lot of null effects here. And even a little warning here about harm effects. So what happens with this is that this pre-registration, and you will see when I talk about that later on, but this kind of approach of open science is forcing researchers to be very, very mindful of how they plan studies and be well prepared and come up with a hypothesis before you do the study, which is the standard in science, but there are news announcing researchers who have been found to fabricate data, to do p hacking, harking, all these practices that are questionable practices. But I'm gonna deal with this later on. But basically, what this is showing this plot is embracing those practices forces you to be a better researcher, and also kind of calm down all the the positive findings that were happening before that. So that's like saying, okay, now we do this, we start to find more null results, and it's simply because we are now being more cautious and more careful about how we conduct the studies. Okay, now let's talk about the pre-registration initiative. Okay, so these are perhaps the two classic papers in this field, PNAS 2018 and this one from 2017 in Nature Human Behavior. The big push behind these kind of approaches or this initiative has been Brian Nosek, as you can see here too. And again, you see John Ioannidis. So these are the first papers promoting this approach of pre-registration and open science. Okay, so what is pre-registration? Okay, this is a graph from this paper from 2016. It's called Pre-Registration in Social Psychology, a discussion and suggested template. Okay, so let's go step by step. Let me see if my animation might work here. If it does not, I really apologize. But okay, I'm not gonna do it with the pointer, the laser pointer. Okay, so this one that you see here is the classic path to research. You theorize, you design your study. Of course, you don't pre-register, just carry on, collect data, analyze the data, write a report, submit it to the journal for peer review. The reviewers evaluate everything, the theory, the design, the analysis, the conclusions, and they make a decision of rejecting, which is the most likely, revise, okay, and perhaps the very less likely is to accept it as is. I mean, it has to be a fantastic paper to accept it, to be accepted immediately. Usually you're sent to revise. No, usually you're rejected, or you're given the chance to revise your paper. All right, so that's a typical approach to publications. Now the pre-registration has two approaches, the unreviewed and the reviewed pre-registration. So if we go this path, you theorize, you design your methods, and then what you do before any data collection is that you propose, you can upload it to what do you call it, preprint. So there's a timestamp on your paper, and then you submit it, collect the data, all these things, and then the reviewers evaluate the theory, the design in correspondence to the plan that you had, the analysis in relation to the plan that you had, the conclusions, and then now the chances of being rejected, revised, or accepted are basically very similar, but this one is the most interesting one. Reviewed pre-registration. Theorize, you design the methods, and then you send it for review, and the reviewers check the theory, the design, the analysis plan. So the journal might give you, they might say, okay, your theory, design, and analysis plan is perfect, so you move on this path. Timestamp, go and collect data, carry on, submit again, and then this happens. If they say no, you have to revise your proposal. Okay, you go back to this step here. It's like a loop here until the reviewers are happy with it, and then you move on this way. Now, what happens at this in this kind of pre-registration is that the reviewers evaluate, as here, that everything is in correspondence with the plan that you proposed here, that the analysis corresponds to what you propose here, and so on. So are the methods executed as planned? Are the confirmatory analysis as planned? Are the exploratory analysis labeled as such? Any deviations explained? Yes. So basically you are fine to be accepted. Because remember, you are giving what is called an in principle acceptance. So in principle means that you passed all this part here. Remember, you haven't collected data at this point. Okay, there is something true here. You might have pilot data that you might need for your analysis plan. Let's suppose you want to calculate some power analysis. You want to calculate some effect sizes, so you can collect some pilot data and make it part of this section here, but not the full collection. When the reviewers are happy with your plan, that's when everything all of this happens. And then you're increasing your chances of acceptance, if you notice. You see? If you go through this and they give you the yes, you have more chances that the paper is accepted so long you stick to your plan. Basically, so long you commit to do exactly what you promise here. When you deviate, you start to have chances for revision or rejection. But if you do exactly what you agreed on at this point, basically everything will be fine. Ah, well, yeah, the animation was working. So that's the traditional way, and this is called the unreviewed pre-registration. This is the review pre-registration. Look, I have done this myself. I have a couple of papers that we reviewed with pre-registration, and it takes some effort. It takes some effort because most of the times they require what is called a power analysis, which is okay, how many people do you need for your study? I'm talking about behavioral studies, psychological studies. I wouldn't know how this will go for the case of statistical research, because in statistics you tend not to need participants unless you want to compare, for example, the performance of a machine learning algorithm with human performance. Let's suppose you want to compare how this algorithm classifies images, the accuracy, and you want to compare that performance against humans. In that case, you would need a certain amount of participants, so you need to run a power analysis. That's kind of a basic requirement at this stage. But if you're just going to use simulations, I would say at this point it's just saying, okay, this is the theory, this is then the simulation design, and this is how we plan to analyze the simulations. That's it. Send it to a journal, they might give you feedback on this, and once they say yes, basically, if you stick to what you said before, you're gonna be accepted. That's it. Accepted regardless of your findings supporting or not what you predicted. That's the interesting part. Because you might think, okay, we foresee that statistical method or algorithm A is gonna be better than B, and then when you do all of this, you find that actually B is better than A. That might be the case. However, it's gonna be published as is because you promise you stick to your plan, and then you did it. If you found something different, well, bad luck, but you follow your plan. You followed your plan. All right. There's a nice article. It's called Open Science Challenges, Benefits, and Tips in Early Career and Beyond. I highly recommend it. It gives you tips, particularly when you're supervising students or you have even like for bachelor students. It's good. It's a good read for them to start thinking about these issues because I really believe, I forecast that this topic is not gonna go away. It's not gonna go away. It's like the internet. We'll never be without internet. We are never gonna be without open science. I think this is the way forward. And there will be bigger pushes by funding agencies, by universities, especially in Netherlands. That's a big thing now, and Netherlands is very serious about open science. This paper is interesting. It's called Data Sharing Policies of Journals in Life, Health, and Physical Sciences Indexed in Journal Citation Reports. This is from 2020. And what it shows is this. These are the quartiles of journals. So Q1 journals, Q2 journals, Q3, Q4. IF stands for impact factor. So obviously the Q1s are the highly repeatable journals. Q2 are okay. Q3 and Q4. So we know this because universities here kind of encourage you or not or push you to submit papers and to publish in Q1 journals. But look at this. The probability of not having policies around open practices are not having policies are lower in Q1 journals than Q4 journals. Now, look at the probability of having strong policies about open science. Higher in Q1 journals, lower in Q4 journals. So basically, the message here is that Q1 journals, or what you can call good journals, are becoming more strict, have strong policies in relation to open practices as compared to Q4 journals. These images are from a blog. It's by Wagenmakers and Dutlet. It's called 7 Selfish Reasons for Pre-Registration. The message is that pre-registration does not prevent researchers from conducting and presenting exploratory analysis, but it does prevent them from unwittingly presenting an exploratory finding as if it had been confirmatory. That's a very good quote from that blog. Basically saying, look, you promised to do a t-test, for example, and then for some reasons you found the samples were not normally distributed and you decided to use a non-parametric permutation test. Okay, you did a different test. That test was not planned. The non-parametric was not planned. It's a new test, so the result can be reported as an exploratory analysis or a supplementary analysis. And you can comment on it. However, you have to stress that it's a supplementary analysis or an exploratory analysis so the reader knows that that was not the test you planned. Even if that test gives you a nicer result, that was not the test that you planned. You planned the t-test. So that's the test that you have to basically comment on, but the other one is presented as an exploratory supplementary analysis. Okay. So these are the images. So the advantages. These are the advantages of the selfish reasons why pre-registration should be done. So the first one is you take credit for your predictions. Like I said before, when you pre-register your study to a journal, you have to highlight, you have to outline your predictions based on the design and all these things. You have predictions, hypotheses. So it's very cool to see that your hypothesis in the end worked out once you collect the data and you have the green light to do so. It's an experience the excitement of waiting for the results. Then you have to prevent the data from taking you hostage because that happens a lot. Look, we have data and then I'm thinking about the situation where you don't pre-register, the classical approach of research. You plan everything, theorize, go collect data, you have the data, and then you start to force the data to meet your expectations. And this is what happens. However, when you pre-register, you say, look, I'm going to do a t-test. It happens that you do a t-test, you didn't find what you expected because you found out after that a permutation test was better. However, you can feel okay with that because, okay, I planned for a t-test, the data was not suitable for a t-test, so, well, it is what it is. So the data is not taking you hostage. You made a decision already. So later on, you might use in a future study, you might go directly for the permutation test because you now have the experience of what happened. Okay, the OSF is the Open Science Framework. It's like the typical place where you upload codes and data. Yeah. Well, you feel good with yourself knowing that you have been honest. You are not playing with the data, you're not manipulating data, fabricating, and so on. Like, this is what I planned. The reviewers gave me a green light. I collected the data, didn't find what I expected. Well, that's it. That's it. Nothing to be ashamed of. That's it. Remember that I talked about in principle acceptance? That's a nice thing. That's a very nice thing, and it's actually comforting because it's saying, okay, I'm planning this. This is my design. The reviewers gave me a green light. Carry on, and that's it. And it's being accepted in principle. And you protect yourself from postdoc critique. Now let's talk about reproducibility, replicability, and robustness. These are the 3 R's. And I'm referring to a paper. It's called Replicability, Robustness, and Reproducibility in Psychological Science. And actually, I'm pretty sure this paper has been published recently. I'm gonna find, yes. I'm gonna show you the actual publication. Just let me know if you can see it on your screen. I guess you're seeing this, I suppose. It's in the journal Annual Review of Psychology. I'm gonna try a different screen in case you cannot see it. It's this one. And I highly recommend this paper. It's very, very good paper. Really good paper. And then you see why I like this paper so much. Yeah, it was published just in October this year. I can see from the journal site. All right, so concepts in the open science. So the first one, replicability, is the reliability of a prior finding with different data. Okay, so you can have a conceptual replication, which is they call it generalizability test, or okay, that's it, conceptual replication. Reproducibility is the reliability of a prior finding with the same data and an analytical strategy. That's basically when you give me your data, your R code to analyze that data. I run the code on the data and I find exactly the same. So I can say I reproduced your findings. I reproduce your findings. Different when I say replicate your findings. If I say replicate your findings, it's because, okay, I'm going to collect data. I'm going to follow the experimental approach that you suggested in your paper. I try to find a sample of the same size, the same gender ratio, and so on. Same stimuli if I can that you use. Everything as close as possible. And then I can say I replicated your study. Another approach, which is this one, the conceptual replication, is I want to replicate the main idea. So your idea, for example, is that people tend to like colorful items more than items in scale of gray colors. That's your finding. And for your study, you used images. That's images, pictures. Pictures of a dog, a cat, a flower in color versions versus the grayscale version with participants. I can say, well, I'm gonna use paintings, and I'm not gonna do the task over the computer. The person is gonna go to a museum, for example. Is gonna go to exhibition center where I have in one room paintings in colors, in the other room paintings in scale of gray, and ask people to give some ratings about the likability of the paintings. For example, that would be a conceptual replication. And the third concept is robustness, which is reliability of a prior finding with the same data and different analytical strategy. This is interesting. Is okay, you give me your data from your study and you give me the R code that you used. And I run the code on the data and I can reproduce it. That's fine. Now, like I said before about the t-test and the non-parametric permutation test, happens that I can see that your data would be better served if it's analyzed with a non-parametric test because I found out that, for example, many of the assumptions for the t-test are not met. Data are not normal. There is presence of heteroscedasticity. So in that case, I can say, all right, I'm going to use a non-parametric permutation test because it's more suitable for your case. And I happen to find that my analysis gives me the same result. So I can say, okay, so your data seems to be robust. So that's a robustness test. This is a classic paper from 2005 using a familiar name, Ioannidis and Brian Nosek. This was a big critique to papers in neuroscience, why most published research findings are false. And this was perhaps the first paper that stirred the situation, stirred the conversations about open science and reproducibility. This one came out in 2018. It's a longish paper. It's has a commentary and has responses from different authors and has a comment from the main authors. It's about making replication mainstream. I'm just showing you some of the key papers in this area. This one came out in 2020. It's called The Reproducibility of Statistical Results in Psychological Research, an investigation using unpublished raw data. This paper was, in my opinion, was painstaking to read because I could see the pain these researchers went through to make this paper. And you can see it here. We were unable to successfully reproduce the underlying statistical results for almost 1/3 of the identified conclusions. Moreover, around 5% of these conclusions do no longer hold. Successfully reproduced conclusions were often the result of cumbersome and time-consuming trial and error work. And really, when you see the paper, you can see that these authors went through this. It was a cumbersome and time-consuming trial and error work, suggesting that the prevailing reporting style in psychology makes verification of statistical results through an independent reanalysis at least hard, if not impossible. This paper is fantastic, really. These guys went through a lot of effort just to make this claim, which seems a simple claim, but they demonstrate it empirically. It's fantastic, really. It's a fantastic work. And it's a big call out to research in psychology and has repercussions to other fields. It's basically, look, when you do your studies, keep a record of everything. Keep your data set in the last version, in the original and last version that you use, particularly if you have the raw data and you apply some R code to pre-process the data before the analysis. Keep the code, keep the original data so that anyone can reproduce it. You see, that's what happened here. This is about tokenize, it's about reproducibility. Basically, keep records of your experimental items, keep records of everything so anyone can reproduce it. Because later on, this kind of data can be used for a meta-analysis, for example, can be used for something bigger. And of course, that means your paper will be cited because it's something that can be reproduced. If it cannot be reproduced, it's unlikely to be cited. This is an example from Australia. It's from the University of Melbourne. They call it the RepliCats project. CATS stands for Collaborative Assessment of 4 Trustworthy Science, and that's the main objective that they have, which is project is to aim to crowdsource predictions about the credibility of published research in 8 social science fields: business research, criminology, economics, education, political science, psychology, public administration, and sociology. This one is a big thing, and it's happening at the University of Melbourne. And you can see that it's big because of this. The RepliCats project is part of a research program called SCORE. It's funded by DARPA. And I assume that you know what DARPA is. So DARPA is the Defense Advanced Research Projects Agency in the US, and those guys are doing like research from the 60s basically, and they fund a lot of research on AI and machine learning and all these things. But to see that DARPA is now caring about this, as I think that says something about what research is going to be in the future. So you can find more information just typing on Google the Replicats project and you find it, more information about it, because it's a very cool initiative. Okay, so what are the approaches to enhance the 3Rs? So reproducibility, replicability, and robustness. Well, the first thing, and this is a personal take of mine, I would say in psychological sciences, at least, is to have a many lab studies approach to research. I got inspired to this after reading this paper from 2010, which basically says, look, we have different cultures, different languages, different ways of thinking. Why do we in psychology tend to follow what the American research says, the research with English speakers says? Why we have to stick to how the brain works based on the research from the UK, research from United States? We can do better. We can try to replicate the findings across different sites to see if that holds. So we can say, okay, let's run a study in Australia. And by Australia, I mean in Adelaide, in my city, with 50 participants. What about translating the items, for example, if they are texts, translating them into Japanese and get 50 people in Japan to do exactly the same task? Now we have 2 data sets. What about doing the same in Indonesia and so on? So we have data from different places. And then, like I said at the very beginning, we can enter the site as a covariate, as a fixed effect. I'm thinking of a regression model as a fixed effect or as a random effect in a multi-level linear model, for example. So you see, but you account for that variability. And if the variability is low, that means, or very low, that means that you can generalize. Well, with certain restrictions, of course, depending on how many countries you have, how many people, and so on, how many items. But it gives you like more confidence on your findings. But everything started from this paper. Highly recommended. These are tools for online studies. Then again, I'm referring to psychological sciences. These are free tools, like for example, GS-Psych. Experiment is another one. It's a Python library. There is something called Gorilla. And there is another one called PsychoPy, which is based on Python. There's a study that came out last year. It's about comparing how these different tools perform. And I think they found that PsychoPy is just totally fine. Now, this one is an initiative happening in psychology. These guys have, I don't know how many people they have, but they have many people from different parts of the world involved in research. So what they do is exactly what I said about the many labs approach, but they do a big scale. So when I do my studies using the many labs approach, I tend to have, I have collaborators in different places, in Colombia, in Australia, obviously, in Japan, in France, in Italy. So I send an email to all of them saying, look, I'm planning to do this. Are you keen to join? If you're keen to join, okay, we need this many people per site, and so on and so on. So I do it like my version, my small scale. So it might be like 5 laboratories, 3 laboratories, 10 laboratories if I can. But these guys, they do it like, I'm talking about 20 laboratories, 25 laboratories in different places of the world. And they announced their initiative in 2018 in this journal, Advances in Methods and Practices in Psychological Science. So if you have the chance, have a look at this paper, because you might think, okay, how can we do, for example, statistical science accelerator or mathematical science accelerator? How can we do that? How can we interpolate or translate this initiative that happened in psychology to our field? Do we need it in the first place? Are we totally fine? We don't need to do these things because our samples are basically the same everywhere. Our simulations will be the same anywhere, everywhere. We don't know. But just give you some food for thought, I think. This is some sites for, again, psychological science. If you want to collect huge amounts of data, for example, Amazon Mechanical Turk is a good place. So, for example, you can, in a week, of course, you have to pay for it for participants, but you can easily collect 1,000 people, 2,000 people. And one of the best examples is this paper that came out in 2018 in Nature. It's called the Moral Machine Experiment. The lead author is a guy called Ilya Rawan, he's a computer scientist. He's now at the Max Planck Institute. And he's doing research on how humans interact with AI or humans interacting with machines. But for this study, look at the sample size. This platform gathered, let me see if I can highlight actually. No, yeah. This platform gathered 40 million people. In my view, that's a very decent sample size. 40 million people in 233 countries. This paper is excellent, because these guys, of course, feel more confident to make generalizations. The study was about how people reason morally about information given by AI. And the findings are fantastic. And if you read the paper, you see why they feel comfortable generalizing, because look at the size, sample size, 40 million people, 10 languages in 233 countries. I think that's pretty good. Now the last bit is measurement, measurement, and measurement. So, like I said before, referring back to the field of learning analytics, has the word learning in it, and this leads to psychometric, because that's what psychometric is about. It's about measurement of the mind in any aspect, and including learning. And psychometrics is just the measurement of psychological processes via testing and assessment, which is very close to a concept called psychoinformatics. It was published in the journal in 2012 in the journal Current Direction Psychological Science. And this is a paper that came out in 2020 in Advances in Methods and Practice in Psychological Science, and it's called measurement, questionable measurement practices, and how to avoid them. It's like a call out for psychometricians, how to do things properly when it comes to doing unquestionable measurement practices. Now, what's besides other things that can help you to reduce questionable research practices? Well, trying to tackle low power, trying to avoid p-hacking, and trying to avoid hacking. So some solutions are what is called multiverse analysis, robust and novel statistical techniques, and provide both explanatory models and their predictive power. That's my suggestion. So you know the p-hacking is when you start doing tests, different tests, or select those that were give you p-values below an alpha level that you follow. Could be 0.05 or 0.005. And hacking is hypothesis after the results are known. So it's like, okay, you get the results, and suppose the results contradicted your theory, and then you amend your theory based on the results. This is what happens with big data. So there's something called the big data hubris. The implicit assumption that big data and fancy analysis and methods, for example, machine learning, allow relaxing principles of scientific rigor, such as measurement, construct validity, and reliability. And this from this journal, from Science in 2014. But also recommend this book chapter. And this is from the book chapter, some of the defining principles of robust science and their implications for big data research. It has to be relevant, rigorous, replicated. It's a description here and the implications for big data. Other topics are, has to be accumulative and cumulative, transparent and open. That's the stress of the talk today, theory oriented. Now, this is a warning for those who are into data mining. Because big data analytics have a natural inclination toward quantitative empiricism, the underlying philosophy often encourages data mining, which is probing data for unplanned or unanticipated relationships to generate insights post-hoc. That's one of my criticisms to people doing machine learning. They just chuck in as many algorithms as you can to make sense of messy data. Because remember, most of the data that is being used in mining techniques, data mining, is observational data. It's never experimental. Experimental data, you obtain it from experimental psychological experiments. This data is like, okay, what the internet has, let's download everything and see what happens if we try these algorithms. This is the multiverse analysis. You might know this name, Andrew Gelman, statistician. He's behind this proposal, which is saying basically, like I said in several occasions before, I have this data and I feel I want to do a t-test, but I believe a permutation test might be better. So in my proposal, my pre-registration, I can say I'm going to try both. How? Why? Because I'm endorsing a multiverse analysis. Okay. So multiverse analysis allows you to look at data from different angles that are sensible and are educated. And are educated, not uneducated, are educated. So this is what happens with the multiverse analysis. This is the traditional approach. You have all these ways to analyze your data, but you report the one that is the most beautiful, that makes you look good. This one is the plant analysis. You say, I'm going to analyze data with a t-test, and that's what you show. But this requires to be very, very honest. This one is the multiverse analysis, which says we plant all these analyses, we show them all. We show them all. And this graphic is taken from this paper. It's a conference paper. I highly recommend it. This one. This one. Who is here? Statistician. This guy, E.J. Wagenmakers, is a patient statistician, psychologist. Basically, what it shows is that they sent a data set to different researchers, asking them a simple question, and they came back with different ways of analyzing the data. Different ways. It's an interesting paper. These are other papers that I recommend. Again, I think Wagenmakers, Andrew Gelman, yeah, he's involved in this one. Wagenmakers, another methodologist, Richard Mori, or another methodologist, and it's saying multiple perspectives on inference for two simple statistical scenarios. It's then again about this idea of how people can have different approaches to analyze data, one data set. I'm very keen on this approach. It's called Robust Statistics, Robust Methods, and it's a nice paper. It's a nice tutorial by Ron Wilcox. I don't know if you know him, statistician. He's a very strong advocate of robust statistics. And this perhaps my preferred approach at the moment is called distribution and regression modeling. It's called GALMS, Generalized Additive Models for Location, Scale, and Shape. It's a very cool approach, very, very, very strong, very powerful. And I like to talk about it in more detail, but it's not the right time now. I can do it for a different talk, but it's just fantastic. And I'm working with people in this field. I'm working with Fernanda Bastiani at the moment on a couple of things in relation to this approach. And this one is like a big thing because this refers now to machine learning, which is the big push in machine learning about predictive model, which bottom line is just performing cross-validation. That's it. So imagine that you have a t-test, you can cross-validate it to see the predictive power that it has. That's it. That's what they're doing. But it's something that is being required these days and being asked these days. Other things are prediction surveys, which is having people predicting hypotheses. Let's suppose you have a prediction that algorithm A is going to be better than algorithm B based on their mathematical properties. You can actually get a bunch of collaborators or experts in the field to predict before you run any simulation based on the information that you give them. This is the mathematics for algorithm A. This is the mathematics for algorithm B. Based on this information, how likely is that this method is better than this one? And you get a survey, and you can put in your article as a prediction survey, and then you test your algorithm and see what happens. It's a cool approach, I think. So this paper actually shows how this has been done. So the conclusions are: embrace open science, which means striving for addressing the 3 R's: reproducibility, replicability, and robustness. Use newer statistical learning methods like robust statistics and distributional modeling, and adopt multiverse analysis, which is time consuming but it's very enlightening, which is analyze data in different ways. So for example, what I'm doing these days in my research is, let's suppose I want to compare 2 groups. I say, okay, I can use a t-test. I invite a colleague of mine who is expert in non-parametric statistics to do a non-parametric analysis. And I invite a Bayesian statistician colleague of mine to run a Bayesian t-test and see what we find. We have now 3 sources of information, 3 different analytical approaches, and see if the pattern holds. And you report that in the paper. Other things that I didn't mention, for example, is to be just honesty and humility in your research. It's something called constraints on generality. You can look it up on Google. Just type constraints on generality and you find a nice paper about it. Consider experimental approaches in order to have control and knowledge of the data generating process. And if you're going to use AI and machine learning algorithms, try to use explainable algorithms. But it's funny because this one goes back to using things like GLM. It's funny because I've seen papers in machine learning where they say, oh, we use a white box algorithm. So instead of using a black box algorithm like a deep learning approach, the white box is, they say we are using a white box algorithm. And when you look at the paper, they just used a GLM with a special tweak in the optimization or something else. But it's a GLM. Interesting. That's why I say statistics has a huge role in machine learning. And that's all for now. So please feel free to send me any question. I'm gonna put my email. You should be able to send me your comments, feedback, questions. If you want to do collaborations, I'm very keen on collaborations on topics that you find interesting from my talk. And just let me, I suppose you will be able to see my email here. Just wait, I'm gonna put it on the screen. Just trying to fit it on one slide, yeah. So, okay, I'm gonna try this one first. I have 3 monitors here. So that's my email. If you feel like commenting on the slides, you have some ideas for collaborations, you have some ideas for improvement. If you have criticisms, please, by all means. So fernando.marmolejo-ramos@unisa.edu.au. I'm going to try different screen just in case I put it in the wrong screen. You might be seeing a black screen or you might be seeing my email. So I try again. All right, so that's all. And once again, thank you for the invitation. Thank you to the organizers. And please, all of you enjoy the sessions today. Thank you.
Okay. There is a presentation from Mr. Professor Fernando. This is, I think, an interesting expose from him, presenting some of later statistical and psychology research issue. Was delivered nicely. Some of us may be interesting to statistical research of big data era, especially in psychological sciences. And I think he will say that statistical and psychological sciences goes digitally. I can highlight here that he mentioned that PsychoPy, that is a Python library for psychometrics or psychological sciences, and on some behavioral research or behavioral experiments that's doing online. And finally, I will end this session with closing statement from his quote today. Learning statistic has the word learning in it. This is naturally leads to psychometrics, and he has also stated on his conclusion that statistics is broad rule on machine learning and AI. I think we can put our question will be delivered by committee to Professor Fernando Ramos, or you can check the Twitter from Professor Fernando Ramos on @Marmolejo Ramos on Twitter, and I will send it on chat box. Okay, thank you for your attention for this session, and hopefully we can get some interesting issue for our research here and all of you participants. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Alfian Futuhul Hadi.
We are now going to our last speaker, Professor Marko Vauhkonen from University of Eastern Finland. The keynote speech will be moderated by Professor I-MaGeStiC from University of Jember, Indonesia. Ladies and gentlemen, please welcome Professor Marko Vauhkonen and Professor I-MaGeStiC.
Thank you very much. Good afternoon, everyone. We will continue to the next speaker. Yeah, this is the last, but yeah, the rule is people say the last but not the least. Yeah, Professor Marko is now yeah in the University of Eastern Finland. Yeah, and he is, I think, shortly his expertise in mathematics and physics. Yeah. And he has now already produced has written more than 110 scientific papers with or in high factor journals. Yeah. And he also currently already supervised more than 20 PhD students, already has 10 inventions and 9 patents. That's very great. Yeah. We are very sorry. I'm very sorry for Marko, because your CP are too long. Yeah, so that may be the short one. Yeah, so yeah, we are very glad. Yeah, very happy to have you here. And I believe that a friend of mine said that your time is 5 hours behind our time. So it's very early morning here there at the moment. Yeah. So again, let's us welcome Professor Marko. I'm very sorry I don't pronounce your name properly. Yeah, Prof. Marko Vauhkonen. Yeah, Vauhkonen. Yeah. Okay. Let's have Prof. Marko deliver his speech now. And again, yeah, welcome to Jember also, although it's not really visiting Jember, but in the virtually. Yeah. So again, yeah, please, Marko, you have about, I think, about 40 minutes to talk, and then we have 20 minutes to have discussion. Please, the time is yours. Yeah.
Okay, thank you for the kind introduction. I try to share my screen for the talk. Should be this one. Yes, and thank you a lot for giving me this opportunity to talk in this conference. So my title is electromagnetic flow tomography. And as said by the organizers, it's 6:30 here in Finland, so I just woke up a couple of hours before, so I try to stay awake. So this is a kind of a common work that we've been working for several years with my colleagues, former postdoc Ossi Lehtikangas and currently Professor Aku Seppänen, and my PhD student from the organizing university, Muhammad Chiaul Arif. He was supposed to moderate this, but they just got a baby this morning, so he's in hospital currently. So hopefully all is fine there. Okay, here's a bit of outline. So kind of reasoning for doing this kind of thing called electromagnetic flow tomography is given first. And it's a kind of classical inverse problem. So I will explain what it is, how we form the forward model and how we solve the forward model, and also how we solve the inverse problem. That's next. Then I show some simulation results and experimental results. We also have designed and built a measurement device for this problem. So I will show some experimental work as well. Okay. So before going to the task, so I just want to show this is nice, these virtual conferences nowadays. So I hope you can see this hand here. So you are somewhere here, or most of you, and I'm up here in the eastern part of Finland, in the city called Kuopio. But no worries, things go fine as well in this way. And here we have a fairly large group on computational physics and inverse problems. So we have a total amount of 5 professors, a few senior scientists and postdocs, and depending on the year, it's around 20 PhD students and some technical personnel. And we work on inverse problems and develop mathematical models and especially computational methods for solving these different types of inverse problems arising from real-world applications. And one of the biggest fields is many types of tomographic imaging techniques, either in medical field or in industrial applications. So that's one large field of inverse problems that we are working on in our team. Okay, I could start by introducing the background physics of electromagnetic flow tomography. And before going to the actual tomography, I would like to introduce electromagnetic flow metering that has been invented, I don't know, about 100 years ago. It's based on very simple physical principle that we all know from high school, hopefully. So it's based on the Lorentz force fact. So that if you have a conductive fluid flowing in a pipe, for example, and you apply external magnetic field going through this conductive fluid flow. So this Lorentz force law says that this system creates electric field or electromotive force across the pipe. And you remember all these finger rules. So if your flow is in this direction and your B field is this thumb, so then the electric field is perpendicular to the both of these fields. And based on this, when you apply this known B field and measure voltages across the pipe, you can calculate the average velocity inside the pipe flow. So this is the basics of the electromagnetic flow metering. And as we check this a bit more mathematical way, so the Lorentz force is written down here. So it's charged times the velocity fields times the external B field. And if you calculate what is the voltage that you measure on the surface, it's of course a line integral of the electric field that is created from the electrode 1 to electrode 2. And if this V field and B field are perpendicular, then this E field can be replaced by V times B. And if B is assumed to be constant, you can take it out from here, and then you rewrite this in this form. So then you get the average velocity field along this line here. And this is actually what is measured in standard electromagnetic flow meters. And it's a simple calculation here. But this is some drawbacks that we would like to kind of improve. It only gives average flow velocities. However, if we are dealing with, for example, multi-phase flows, we have certain kind of flow profile, or actually all the cases we have some kind of flow profile. So the flow velocity changes in different parts of the pipe. And this is extremely important, especially when you're interested in multi-phase flows. And if you're interested in measuring how much certain material flows through the pipe, for example, if you have water and oil and some solids and gas, so the question is how much oil or solids travel through the pipe section in certain amount of time. And for these calculations, the average flow velocity might give results that are fine, but normally they are quite erroneous. Also, this assumption here assumes that B field is constant across the pipe section, but that's not always the case. It's difficult to create extremely homogeneous and uniform B fields. Also, if you have half full pipe flows, that means that you have conductive fluid that fills only certain part of the pipe. It may happen that your electrodes are in the air. So in this case, this kind of technique doesn't work. It doesn't measure any voltages in the air. It has to be in contact with the flowing fluid. So that's why we started to study the same principle, but doing that in tomographic manner. And what it means, it's based on the same physical principle, it's fine. But what we do when we create the B field, we use more coils so that we can create different types of magnetic fields. And also, in order to increase the amount of data, we do these voltage measurements on the boundary in several different locations. So for example, here we have 4 coils in our prototype system, and then we have 16 electrodes. You cannot see them because they are underneath these coils, but they are attached on the surface of the pipe. And when you make these voltage measurements, you not only are able to estimate the average, but you are able to estimate the flow field, the tomographic image of the flow inside the pipe. Okay, so this is the physical idea behind this. And of course, here you have to have also conductive fluids. But it doesn't matter if some of the electrodes is in the air, because you can use the rest of the electrodes to estimate the flow field. And also, B field doesn't have to be constant. You can calculate it basically analytically what it is, and then you can plug that knowledge in your code, in your algorithm. Okay, so let's have a look a bit of mathematics, how to model this kind of a system. So everything starts from Maxwell's equations, basically, when we are dealing with electromagnetics. So they are written down here. So standard notations: H is magnetic field, J is current density, E is electric field, omega is frequency, angular frequency, and epsilon is permittivity. We can actually only look at this one. You can ignore that one. And physics says that current density can compose or is composed from several different components. So there's ohmic current. This is conducted times the gradient of the voltage field. Then there might be current sources inside the domain. And then there's a other current source that is created by this Lorentz force caused by this flowing fluid and the external B field. And now the trick is to take the divergence of this curl, which is always 0, as we know, then plug in this J in here and assume that this angular frequency is 0. We use very low frequency currents when we create the B field. So it's a proper assumption. So we end up in this equation. There's still this applied current inside, but we don't have any sources there normally in the pipe. So this is our mathematical model for our electromagnetic flow tomography. And simply, this is a PDE, partial differential equation, that can be solved in general numerically. We do it with finite element method. I will show you next how it goes. And the so-called forward problem is when you know the velocity field V here and the applied external B field and the conductivity inside the pipe, you can solve the potential field, and then you can solve any possible combination of measuring voltages on the boundary as well. So this is the forward problem. And the inverse problem from this equation is, of course, so that you measure your voltages at some points on the boundary, not inside at all, only on the surface of the domain. And you know the B field and conductivity, these are simply known, and then you try to estimate what's the velocity field, velocity distribution inside the domain omega. Okay, so a few steps to derive the discrete form. I try to go this through quickly. So standard Galerkin approach, FEM approach to first creating the variational form. So we multiply this equation by a test function. It's phi here and use Green's theorem. So we get the left side like this and the right side like this. Very standard approach, nothing here special here. And then we apply boundary conditions. We make assumptions that may not hold depending on how you cut your computational domain. But if you have long enough pipe section, this omega to be modeled. So these are pretty much valid. So we assume that there's no current flow out from the domain. Of course, we normally have a plastic pipe surface, so there's no current flow through. And we also assume that our coils are pretty far from the ends of the pipe, so there's neither current flow through the ends of the pipes of the pipe. Also, velocity field is assumed to be 0 on the wall. This is physically true, basically. And also we assume that B field is 0 at the ends of the pipe. So plugging these in here, we get rid of these boundary integrals. You might be able to use some other boundary conditions, but that's what we do. So we end up having this kind of variational form. And again, we proceed with the standard Galerkin approach. We use piecewise linear approximation of our potential field, and then use the same test functions as the basis is chosen here. So piecewise linear. And we write the velocity field that we are approximating or estimating in our inverse solution in this form. So it's also piecewise linear with 3 different components. Actually, as we will see next, we make an assumption that the Vx and Vi are 0. So there's only component that is on the same direction as the pipe axis. This we need to do because we actually don't have measurements enough to estimate these X and Y directional components. Okay, but otherwise this model holds for any type of velocity field. And when you plug in those approximations and the test function to there, you end up to this kind of a discrete form. So this is the left-hand side. U is a vector form of the potential field, so values on the nodes of your finite element mesh. And then the right-hand side can be written in this form. So there's some matrix D times the velocity field, including the X, Y, and Z components of this vector field. Okay, so here are the details of those matrices. I don't go through those, and actually these two with our choices can be ignored because only this is assumed to be non-zero. These are zero, so what is needed actually is this dz finally. So it's written down here. So we estimate from our measurements actually only tomographic image, so only on the cross-sectional level where your measurement electrodes are. So we make one more further assumption that the z-directional velocity field remains the same in the whole pipe section. So this is a two-dimensional vector that we extend using this kind of a projection operator to the whole pipe domain. So this dz projected times v is the right-hand side, and then we invert this A matrix, and we finally get this potential field solved. So A inverse times this is of course this U vector here. And then we need another operator or matrix in practice, this M here, that samples, formally speaking, samples the measurements on the electrode. So this is a vector that includes your actual measurements when you know what's the velocity field and when you know what is the applied B field. So this is a discretized version of the forward model that is written down here. So measured voltages is some matrix that depends on the B field and the conductivity distribution times the unknown velocity field. So now what we are interested in doing is to solve, of course, the unknown velocity field when you have measured the created voltages on your measurement electrodes. And this is the solution of the inverse problem. And there are, of course, lots of different approaches. We are mainly in our research group interested in using this kind of statistical Bayesian framework where everything is kind of assumed to be statistical. They have probability distribution and such. And since we have to apply some prior information, solving this V from the measured voltages is so-called ill-posed inverse problem. So we have to regularize it or introduce some prior. And as said, most common way is to do it statistically with this Bayesian framework. And what we actually solve is the so-called posterior density, which is the density of the velocity field given the measurements. Actually, we could write down that this is proportional to the likelihood density times the prior. And this is, of course, a large dimensional probability distribution. And what we normally do is that we calculate some point estimates. It could be a mean value of this distribution or something else. And the most common is to pick up the maximum of this posterior. So this is what we have chosen in most of our solutions in this case. So we calculate the maximum of this posterior, which is denoted as B map here. And we assume everything is, all those probability densities are Gaussian, so we can write down this also in this kind of minimization problem, where you have this kind of a measurement related part, and then you have your prior part here, and you have some let's say regularization matrix here, and then you have a similar matrix for the noise. So these are actually parts of the covariance matrices of your prior density, and also part of the covariance of your noise assumptions. Quite often these are diagonals. Okay, this can be written in another form. This is equivalent mathematically to this one. There's nothing special here, and this is a linear problem, so we can actually write down the closed form solution, what your system is. So what you need to have here, you have this H matrix here. It's the known matrix from your discretization. That's fine. Then you have your measurements. That's fine. You get them from your device. Then there are the covariances of the prior. We use so-called squared exponential covariance for this Gaussian density, so-called Gaussian smoothness. We don't go into details of it. There are a lot of choices to do that. Then you need some assumption of the mean of your prior. This is also some kind of assumption that you decide by yourself. We normally have some idea what the velocities are, so we plug it in here. This is the mean of the noise of the device. You can actually measure this by doing a repeated measurement, so that's fine. And then you have the noise covariance of your device, basically. If the channels and your measurements are uncorrelated, so this is just a diagonal matrix here. Okay, so this is our estimate for the velocity distribution based on your measurements on the surface of your pipe section. Okay, let's go to some examples. First, some simulations, and then a few experimental results. So as said, these inverse problems are normally and basically always ill-posed, which means that for example, small modeling errors can cause large errors in your reconstruction. And also there can be two quite different, in this case, velocity distribution that produce exactly or almost exactly the same boundary data. So it's difficult to figure out which one of these two distributions has created the data that you measure. So these are the facts in ill-posed inverse problems. And actually here we have a complete non-uniqueness in one case. For example, if you use a B field that is completely homogeneous in your domain, it could be shown that whatever axisymmetric velocity field, for example, like this kind of parabolic and annular here, they produce exactly the same measurements. If the total flow rate is the same in both cases, so the fluid can flow in different locations compared to these when you compare these two. But as long as the amount of water flowing is the same and these are axisymmetric, then the data that you measure are exactly the same. So measuring this with one homogeneous B field, you cannot say whether the distribution is this one or that one. So it's completely non-unique case. But adding more data, you can solve this problem. It's not another problem in practice. So the internal U field look different, but the boundary data is exactly the same. Okay, just to motivate a bit. And here is our simulation setup. So we have simulated actually our own device. So we have a pipe section of length 15 centimeters. We have 16 electrodes on the central part of the pipe. Then we have 4 different coils around here, having 805 windings of copper. And then there are some facts for the finite element calculations. and also for the inverse solution. So we solve the inverse problem in 2D mesh of 581 nodal values. And of course, when we simulate the data, we need to have dense and really dense mesh and add some noise in order to avoid any inverse crimes, so that we don't use exactly the same model in forward and inverse steps. Okay, and then we tested a few different B field excitations, as can be seen with these kind of coils. You basically cannot create any homogeneous B fields with Helmholtz coils, which means that these would be much larger than they are here. You could create basically a complete homogeneous distribution there. Or then you should need to change these to saddle shape or something like that. But if you have standard circular coils, so the B fields are not homogeneous. So we use this kind of Helmholtz type coil where the current flows in the same direction. So the B field is looking like this. So it's almost homogeneous in the whole domain, but not quite. This is the value of the B field. This is the same, just 90 degrees rotated, and this is anti-Helmholtz field, so that the currents flow in different directions. So then they kind of cancel each other in the middle. So basically somewhere here the B field is zero, as can be seen. So let's see what kind of reconstructions we obtain using these kind of excitations. And as said, you can calculate these in analytic way. So that's not a problem. We know what the B fields are everywhere, and we tested this with different types of velocity fields. So one is standard parabolic flow. Then there's completely asymmetric, so-called quartic flow. The first one can happen in horizontal laminar flow, pipe flow case. This could happen in oil water flow and multiphase flows in certain pipe types. Annular could be in the case where you have gas in liquid, and then this kind of asymmetric stratified when you have solids in fluid flow. So let me see. Okay, perhaps they are here. Yeah. So these are the plots of the velocity fields that we have used to create the simulated data. So these are not measurement case, but we have to have some kind of a V field that we use to create the measured voltages, and then we add some noise there, and we use that as a measurement data, and we then invert our system to obtain.
Excuse me, Prof.
Yep.
Maybe you still have another 5 minutes.
Yep.
Okay. Thanks a lot. Yeah, please continue.
Yeah, and then we estimate the V fields. And these are just examples what kind of potential fields we create based on those. Same for different B fields. They are not that interesting. And these are just the results of the different cases. So this is a true, and this is if you use one excitation E1, so one Helmholtz and one anti-Helmholtz. So you don't get any good results. In quartic case here, you actually, since the field is itself non-symmetric, so you get much better reconstruction. But if you add one more B field, so that you have 16 plus 16 measurements, you get quite nice results also in annular and also with parabolic case. And this is the stratified flow, so also quite nice results with 2 excitations. Okay, then a couple of results from our experimental. These are a couple of pictures of our device. So this is basically similar to what we have simulated. So we don't go into details. And this is just a graphical user interface of our device, so we can control a lot of things in this device. And the measurements look like this. We can use sinusoidal or this kind of a DC excitations to the coils to create the B field. And again, similar excitations. One Helmholtz in this direction and the other 90 degrees to the first one. Okay, then a few simple test cases. We tested with the open pipe so that there was nothing in the pipe, just a water flow. And then we put this kind of a blockage in here. It means that the flow field is faster because it must go through the smaller hole. And the reconstruction is shown here. So it goes nicely as the theory says. And then another simple case, another blockage, again, because the amount of water flowing here is the same as with the open pipe. So it must flow through this smaller hole here, so the velocity increases in here. So this is the reconstruction of this measurement case. And then finally, a couple of multi-phase flows. You have water with solids here, and the distribution is here, and this is inclined pipe, so velocity is lower down here. That's what theory also says. So we can see that here it's around 0.3 meters per second, and up here it's around 1.1 meters per second. And this is oil water flow, and similar effect is here, and oil here due to the viscosity has lower velocity. So these are reconstructions from the real experiments. The final thing was that we estimated the average value with our device and then compare it to the ultrasonic device, and the correlation is quite nice. With higher velocities we get a bit lower results than the ultrasound measurement device. Okay, so just few conclusions. So it shows that we are able to estimate these V fields with simulated data and also with experimental data. And what we are working on now, especially with Arif, is to combine, and we've done this, combine two different techniques to estimate the volumetric flow rates of the materials. And then we have also developed dynamic estimation techniques using Kalman filter approach. And here are some references if someone is interested in reading more on this. And thank you for listening, and I would like to thank our financiers of this project. If there are any questions, so I'm happy to try to answer.
Okay, thank you very much, Prof. Marco. It's very interesting topic, and you have delivered it very patiently. Yeah, I know. Yeah, we have to listen in English, and also the topic is quite maybe for some of us is quite more physical and also high level of mathematics. Yeah. But one interesting thing is you have combined the mathematics, the physics, and recently maybe Bayesian statistic. Yeah, it's very interesting. Yeah. Okay, let us give chance to the audience if there are any question for you. Or let me see. Okay, let me read from. Okay.
Say something in chat.
Yeah, there's one question from chat. Okay. The question is
about the noise.
About the noise. What the noise where the noise come from, and how to reduce the noise. I think that's the question. Yeah, you also can read yourself.
Yeah.
Okay.
Well, well, when anytime you have the actual devices, physical device, so as I skip this very quickly, unfortunately, so I can show how the data looks like. The measured voltages are sub-millivolts, so they are very small, and the electrodes might get dirty. There might be air bubbles hitting the electrodes and such. So these are the actual measurement data. So you can see clearly this is the actual current that we put in the coils, which create the P field, and this creates the electric field, and then we measure these small electric field or voltages on the electrodes. Actually, we measure through neighboring electrodes around the boundary. So due to these practicalities, so in the measurements you always have this kind of a ripple. So this should be, of course, if it was kind of a completely constant, that would be optimal case. But we have here certain amount of measurement noise, and as as I said, these are like, in this case, around 0.05 or 0.02 millivolts that we measure. So they are electronically quite tricky to measure. And same holds, we can use either DC or AC excitation. So the same holds also in the sinusoidal excitation. So you never achieve a complete measurement. So it just comes from the physical facts, and also partly from the noise of the electronics. I hope this answered at least part.
Thanks, Prof. That's the question from Ari Nur Hayati, our colleagues from Physics Department. Yeah, thank you also, Bu Ari. Okay, is there any other question or? Okay.
Not
is there anything Prof want to talk more or explain more before we close this session?
From my side, not really. I'm just happy to have Muhammad Chial Arif here with me from your university, and he's working on these dual modality and dynamic systems. So we've just got nice results from his latest studies, but they will be presented in some other occasion, hopefully by him.
Okay, thank you very much. And yeah, we are a bit unfortunate that Pak Shaul cannot join us this afternoon because his wife just gave birth this morning. Yeah, hopefully everything is very well for them. Yeah. Okay, I think that's all from Prof. Marco, and thanks again, Prof. Marco. And
thank you.
We are very happy to have you here, and very delighted and very insight talk from you. Yeah. I think that's our last session. Yeah. So again, let us give applause to Prof. Marco. Yeah, and for the nice speech and very interesting speech. Yeah. Okay. Then I think I would like to return this session to the MC. Yeah. Okay, please, MC, you can take over. Yeah.
Thank you, Professor Marco Pauvanen and Professor Imade Tirta.
And this is the end of our plenary session. Present link of the participant is provided in chat feature. Please fill the form to get the certificate. Now, we will hold a photo session. To keynote speakers, as well as participants, please welcome to open your camera. Please be prepared to take one. Okay, to keynote speakers as well as participants, please welcome to open your camera. Okay, please be prepared to take one. Take one. Okay, thank you. And please be prepared to take two. Take two. And next, take three. And the last take. Okay, thank you.
Excellencies, participants, ladies and gentlemen, this is the end of our plenary session. The parallel session will be started at 1 p.m. this afternoon.
We hope you have been enjoying yourself at the conference so far. We are very honored to have you with us here. We also hope you have found the presentation on this conference are informative and helpful.
Thank you very much. Please prepare yourself to the next session and take your time. Wassalamualaikum warahmatullahi wabarakatuh.